How can the universe possibly understand its own size without ever reaching for some kind of cosmic measuring tape? Think about that for a moment. We, as humans, are so dependent on tools and comparisons, rulers for inches, satellites for miles, telescopes for light years. We're always looking outward, trying to grasp something that seems forever beyond our reach. But what if the universe doesn't need to measure itself at all? What if, from the moment it began, it already contained the knowledge of its own scale, woven into the very fabric of space, time, and energy? This isn't just a theoretical puzzle, it's a profound reimagining of reality itself. We often picture the cosmos as a vast, silent, and perhaps indifferent expanse, but today we're going to explore the captivating idea that the universe might be more like an intelligent, self-aware system, operating through hidden mechanisms that allow it to sense, define, and even embody its own dimensions. This journey will take us from the mind-bending principles of Einstein's relativity to the fuzzy, uncertain heart of quantum mechanics. We'll see how light acts not just as a messenger but as a living record of cosmic distances, how gravity sculpts spacetime in ways that inherently understand mass and scale, and how the afterglow of the Big Bang itself serves as a permanent fingerprint of the universe's earliest size. We'll even venture into speculative but thrilling territories like the holographic principle, where information itself replaces volume, and black holes, which encode their size with eerie, silent precision. This is more than astronomy or physics, it's a deep dive into one of the greatest mysteries of existence: how reality can know itself from the inside without an outside perspective to guide it. By the end of this video, you won't just see the night sky differently, you'll understand it differently. You'll grasp how the universe's laws form a closed, self-referential loop of awareness, and why something as simple as the speed of light or the pull of gravity isn't just a rule but a kind of cosmic language speaking the universe's dimensions into being. So settle in and open your mind. We're about to rethink not only the size of the cosmos but the very nature of knowledge and measurement. What you're about to discover may forever change how you see your place in this intelligent, self-knowing universe. But here's the thing we so often forget. Every single one of those tools, from the simplest ruler to the most powerful space telescope, relies on a fundamental human conceit. We believe that to know something, we must actively go out and measure it. We project our own methodology onto the cosmos, but the universe itself operates on an entirely different principle. It doesn't need to measure because it never became separate from itself in the first place. Its knowledge of scale is not an acquired skill, it's an inherent, baked-in feature of its existence, written directly into the source code of physical reality. Think about the sheer absurdity of trying to use a ruler for a cosmic distance. Even if you could construct one that was light years long, the universe would foil your attempt before you even started. Space itself is expanding, stretching the very fabric between galaxies. The moment you laid your cosmic ruler down, the endpoints would begin to move away from each other, rendering your measurement instantly obsolete. And that's if you could even see the endpoints. The finite speed of light means we are forever looking into the past, seeing objects not as they are, but as they were. Our entire observational toolkit is shackled by these limitations, giving us only a flickering, historical silhouette of the true cosmos. We are like archivists trying to understand a living, breathing creature by only studying its fossilized bones. Yet, while we struggle with these external instruments, the universe has its own seamless internal system. It doesn't use tools, it is the tool. A perfect example is the Hubble constant. This isn't a number that astronomers discovered and the universe then decided to obey. It is a fundamental rate, the speed at which the cosmos expands for every megaparsec of distance. This constant is not a measurement of the universe. It is a parameter within the universe, a dial setting that actively defines the relationship between velocity and distance. The expansion itself is the process of self-calibration. The universe isn't consulting a map, it is drawing the map in real time, with every galaxy's recession being both an action and a data point in a single, unified act. Then there's the cosmic microwave background radiation, the oldest light we can detect. For us, it's a fossil we dug up, a relic to be studied. For the universe, it's something far more profound, a permanent, all-sky tattoo left over from its infancy. Those tiny variations in temperature, those faint whispers of hot and cold, are the primordial seeds from which all galaxies grew. That pattern is not a record the universe keeps, it is a foundational part of its structure. The universe doesn't need to look back at the CMB to remember its early size. Its current vastness is the direct, evolved consequence of those initial conditions. The past and present are in a continuous, unbroken dialogue, and the scale is simply the current state of that conversation. This reveals a breathtaking truth. What we proudly call measurement is really just our clumsy, external eavesdropping on the universe's own seamless internal processes. We see galaxies moving apart and we infer expansion. We detect ancient light and we calculate distance. We are interpreting a symphony from the faint echoes that reach our ears, while the universe is the entire orchestra, the composer, and the concert hall all at once, perfectly aware of every note and every harmony because it is actively creating them. The cosmos doesn't measure itself, it performs itself, and its size is simply one note in an ongoing, magnificent composition. But if rulers and telescopes are our flawed, external attempts to grasp the cosmos, then what is the universe using internally? It turns out the cosmos comes pre-equipped with its own perfect, immutable measuring system, written not in inches or miles but in the fundamental constants of nature. These are not numbers we invented, they are the universe's own signature, the fixed settings on the control panel of reality that make our universe what it is and not something else entirely. Think of the speed of light, often denoted by the letter c. This isn't just the velocity of a photon, it is the ultimate speed limit of causality itself, the rate at which all information and influence can travel through spacetime. It is the cosmic converter between space and time, defining what a light year truly means and stitching the fabric of the cosmos together with unbreakable thread. Then there is Planck's constant, a tiny number from quantum mechanics that determines the size of the quantum realm. It sets the scale for how energy is parceled out in indivisible chunks, or quanta. This constant draws the line between the smooth, predictable world of large objects and the fuzzy, probabilistic world of the very small. It dictates the size of atoms, the energy of chemical bonds, and ultimately, why you don't fall through the floor. Without this specific value, matter as we know it could not coalesce into stable structures. And we cannot forget the gravitational constant, big G, which dictates the strength of the gravitational pull between any two bits of matter in the universe. It is this constant that orchestrates the dance of planets, the binding of galaxies, and the crushing force of black holes, setting the gravitational scale for the entire cosmos. The true magic, however, lies not in these constants individually, but in the pristine, dimensionless ratios they form when combined. The most famous of these is the fine structure constant, approximately 1/137th. This number emerges from the relationship between the speed of light, the charge of an electron, and Planck's constant. It governs the strength of the electromagnetic force, controlling how tightly electrons are held to an atomic nucleus. If this number were even slightly different, the fusion processes in stars would fail, carbon atoms could not form, and the complex chemistry necessary for life would be impossible. But its role is even grander. It ensures a breathtaking consistency from the microscopic to the macroscopic. The same force that holds a single atom together also, through an immense chain of cause and effect, influences how galaxies cluster and spin. The universe doesn't need a separate set of rules for the small and the large. It has one elegant, scalable framework where size is an emergent property, not a measured quantity. This is the profound revelation. The universe doesn't calculate its size. It doesn't perform some internal cosmic math problem to figure out how big it is. Instead, its size is an inevitable, logical consequence of these fixed parameters. The constants are the definition of scale. The gravitational constant tells spacetime how to curve for a given amount of mass, inherently defining what a certain Schwarzschild radius should be. The speed of light tells us how far influence can have traveled since the beginning, inherently defining the observable horizon. These are not passive numbers waiting to be discovered. They are active agents that continuously shape and define the dimensions of everything that exists. The cosmos knows its size in the same way a sphere knows it is round. It is an intrinsic, geometric property of its very being, dictated by the unchangeable rules of its own existence. Now, let's shift our perspective from these static cosmic constants to the grand, dynamic motion that defines our universe on the largest scales. Picture the entire cosmos not as a static stage, but as a living, breathing entity specifically. Imagine the surface of an expanding balloon. This classic analogy is powerful because it captures a truth that is deeply counterintuitive. In an expanding universe, every single point is moving away from every other point. There is no central point of explosion, no privileged center from which everything is fleeing. The space between galaxies is itself stretching, carrying them apart like raisins in a rising loaf of raisin bread. This isn't a motion through space, it is the motion of space itself, an intrinsic property of the cosmic fabric that requires no external push or pull. This relentless, smooth expansion is governed mathematically by the Friedmann equations, derived from Einstein's theory of general relativity. These equations are the universe's own internal dashboard, displaying the readouts for its density, pressure, and curvature. They don't just describe the expansion, they are the active mechanism by which the universe feels its own scale. The rate of expansion, parameterized by the Hubble parameter, is like the universe taking its own pulse. A faster pulse means a more rapid, youthful expansion. A slower pulse indicates a more sedate, mature pace. By sensing this rate, this relationship between how fast things are moving and how far apart they are, the cosmos has a continuous, real-time awareness of its own dimensions. It's a feedback loop where the contents of the universe, its matter and energy, tell spacetime how to curve and expand, and that very expansion then dictates how those contents will evolve and interact. This is where the Hubble-Lemaitre law comes into play, acting as the stethoscope for that cosmic heartbeat. The law is beautifully simple. The farther away a galaxy is from us, the faster it appears to be receding. The velocity of a galaxy is proportional to its distance. That proportionality constant is the Hubble constant. For the universe, this isn't a law it obeys, it's a law it is. This relationship provides a dynamic, ever-updating readout of the universe's scale. By simply existing and expanding according to its own rules, the universe is perpetually generating the data about its own size. It doesn't need to stop and take a measurement. Its very state of being is the measurement. The recession of galaxies is both the action and the information. a single process that defines scale through motion. This transforms our understanding of cosmic growth from a random, mindless process into something far more elegant, a deeply self-referential act. The universe's size isn't a fixed number written on a hidden placard. It is a fluid, evolving property that is continuously defined and redefined by its own inherent motion. The expansion is the universe's way of knowing itself, of feeling its own vastness through the stretching of its very fabric. It is a silent, ceaseless dialogue between matter, energy, and space-time, where the only output is the magnificent, increasing scale we observe today. This intrinsic, motion-based awareness sets the stage for understanding how light, the universe's ultimate messenger, carries and encodes this information across the vast interstellar distances. So if the expansion of space is the universe feeling its own pulse, then light is the bloodstream carrying that information to every corner of its cosmic body. We often think of a photon as a simple particle of light, a tiny messenger racing from a star to our eye, but on a universal scale, it is so much more. It is a fundamental data packet, a tiny vessel of information that, simply by existing and moving, passively records the history and scale of the cosmos. It doesn't need to be aimed or programmed. Its journey itself is the measurement. The universe's internal communication network isn't built with wires or signals. It's woven from the fabric of electromagnetic waves traveling at the ultimate speed limit. The most profound way we see this is through a phenomenon called redshift. As a photon travels across the expanding universe, the space it moves through is itself stretching. This stretching does something incredible to the light wave. It literally pulls it, elongating its wavelength and shifting it toward the red end of the electromagnetic spectrum. This isn't a change in the photon's speed. It's a change in its very character caused by the expansion of the medium through which it travels. The amount of this redshift is directly proportional to the amount of space the photon has traversed. A greater redshift means the light has journeyed through more expanding space, which means it has come from a more distant, and therefore, in the past region of the universe. The photon doesn't compute this, it simply becomes this record. Its condition upon arrival is a direct, unedited log of its entire epic journey. The universe, in a sense, is continuously writing its diary in the language of light, and redshift is how we read the entries about distance and time. Nowhere is this more stunningly evident than in the cosmic microwave background radiation. This isn't just ancient light, it is the oldest story the universe has to tell. It's the residual glow from when the cosmos cooled enough to become transparent, a flash of light released nearly 14 billion years ago that has been traveling and stretching ever since. That light began as the searing, visible white glow of a plasma-filled infant universe, but after eons of traveling through an ever-expanding cosmos, that light has been redshifted by a factor of over 1,000, stretched from visible wavelengths all the way down to the microwave part of the spectrum. What we detect today is not a brilliant flash but a faint, cold whisper washing over us from all directions. For us, the CMB is a treasure trove of data, a fossil we study to understand the past. But for the universe itself, this background radiation is something far more integral, a permanent, all-sky calibration chart. It is a fixed reference point etched into the fabric of reality at the very beginning. The patterns of slightly hotter and colder spots in this radiation are the primordial seeds from which all galaxies, stars, and planets would eventually grow. The universe doesn't need to look out and measure these structures to know its scale. Their current size and distribution are the direct, evolved consequence of those initial imprints. The CMB is the universe's foundational blueprint, and the present-day cosmos is the constructed building. The scale is inherent in the relationship between the blueprint and the finished structure. No external measuring tape is required. This reveals a universe engaged in a constant, passive exchange of information with itself. Billions of photons are crisscrossing the vast distances between galaxies at every moment, each one being subtly altered by the expanding space it travels through. This isn't an active broadcast, it's a side effect of existence. It means the cosmos is always and everywhere awash in a sea of data about its own dimensions. The light from a distant supernova, the glow from a quasar, the faint signature of a remote galaxy, all of it carries encoded within it a story of how far it has come and how much the universe has stretched during its journey. This transforms the cosmos from a silent, empty void into a bustling network of constant, silent communication, where light acts as both the message and the medium, allowing the universe to be perpetually and effortlessly aware of its own immense scale through the simple, elegant behavior of its most fundamental messenger. But this cosmic conversation of light and expansion is only one side of the story. To truly grasp how the universe understands its own scale, we must turn to the most profound sculptor of reality itself, gravity. Forget the old idea of gravity as a simple, invisible force pulling things together. Einstein's revolutionary insight was that gravity is not a force at all, but a property of space and time. Picture the fabric of the cosmos not as a static, empty stage, but as a dynamic, flexible membrane like a taut rubber sheet. Now place a massive object like a star onto that sheet. It creates a deep well, a curvature in the fabric. This is gravity. The star doesn't emit a force, it simply warps the geometry of space-time around it, and this warping dictates how other objects move. A passing planet doesn't get pulled by an invisible string. It simply follows the most natural path, the straightest possible line through the curved geometry, which we see as an orbit. This elegant dance is governed by Einstein's field equations, a set of complex formulas that are the universe's own instruction manual for how matter, energy, and geometry interact. These equations describe a beautiful closed-loop dialogue. Matter and energy, simply by existing, tell spacetime how to curve. In turn, that curved spacetime tells matter and energy how to move. It's a perfect, self-referential feedback system. The universe doesn't need an external architect to design the orbit of a moon or the path of a galaxy. The mass of the objects and the resulting curvature of space around them contain all the information needed. The scale is built directly into the geometry. A more massive star creates a deeper, wider curvature, inherently defining a larger gravitational domain around it. The relationship is absolute and requires no external measurement. Nothing illustrates this more perfectly and mysteriously than a black hole. According to the field equations, if you compress a certain amount of mass into a sufficiently small volume, the curvature of spacetime becomes so extreme that not even light can escape. The boundary around this point of no return is called the event horizon. What's astonishing is the sheer simplicity of its size. The radius of this event horizon, known as the Schwarzschild radius, is determined by one thing and one thing only: the mass of the black hole. The formula is breathtaking in its elegance. It doesn't care about what the black hole is made of, its temperature, its chemical composition, or its history. It only cares about the total mass. A black hole with the mass of our Sun would have an event horizon with a radius of about 3 kilometers. One with the mass of a galaxy would have a horizon stretching billions of kilometers. The size is an inherent, encoded property. The black hole doesn't measure its own width. Its mass and the immutable laws of geometry dictate its dimensions. It is the ultimate example of self-contained cosmic knowledge, a perfect sphere of darkness whose very existence is a definitive statement about scale. This principle extends far beyond these extreme objects. Every planet, every star, every galaxy warps the spacetime around it to a degree precisely calibrated by its mass. The orbit of our moon is not a random path. It is the direct and inevitable consequence of Earth's mass curving the local spacetime. The size of that orbit is written into the fabric of the universe through this gravitational relationship. This means that on the grandest scales, the cosmos is a vast, interconnected web of curves and dips, with each object moving according to the local terrain. The universe isn't consulting a map, it is the map. Its dimensions aren't measured, they are embodied and expressed through the continuous, silent interaction of gravity, where every single particle of matter contributes to defining the cosmic scale simply by being present and bending the stage upon which the entire drama unfolds. But just as we begin to feel comfortable with gravity's geometric certainty, we are pulled into a realm where all such classical intuition shatters. Welcome to the quantum world, a domain so bizarre that the very concepts of position, size, and measurement lose their familiar meaning. Here, at the smallest scales of reality, the universe operates not with the crisp certainty of a blueprint, but with the shimmering potential of a probability cloud. This isn't a matter of imperfect tools or limited technology. It's a fundamental feature of existence itself. In the quantum realm, to measure something is not to simply reveal a pre-existing property, but to force a definitive outcome where only a spectrum of possibilities existed before. The universe at its heart is fuzzy. This profound truth is captured by Werner Heisenberg's famous uncertainty principle. It states, in essence, that there are certain pairs of properties like the position and momentum of a particle that cannot both be known with perfect precision at the same time. The more accurately you pin down a particle's location, the less you can know about where it's going, and vice versa. This isn't a statement about our clumsy human instruments. It's a statement about the intrinsic nature of reality. It's as if the universe itself refuses to be pinned down to a single, definite state at this level. So how does the cosmos know its properties? Not through fixed values on a cosmic spreadsheet, but through probabilities and wave functions. A particle doesn't have a position until an interaction, a measurement, collapses its wave function, forcing it to choose a location from a range of probable options. The universe isn't ignorant, it's simply playing by a different set of rules where knowledge is inherently statistical and potentiality is more fundamental than actuality. This quantum fuzziness isn't confined to individual particles, it's woven into the very vacuum of space. According to quantum field theory, what we perceive as empty space is anything but. It is a seething, bubbling foam of fundamental fields, constantly vibrating with fleeting fluctuations. Virtual particles pop in and out of existence in a frantic dance, borrowing energy from nothingness for the briefest moments allowed by the uncertainty principle. This omnipresent quantum jitter is not a minor side effect. It is a primary actor that defines the energy density of the vacuum itself. These fluctuations are the reason an atom doesn't collapse. They contribute to the mysterious dark energy driving cosmic acceleration, and they set the fundamental scale for the quantum world. Crucially, this happens completely passively. There is no giant in the sky measuring the energy of the vacuum. The fields simply fluctuate according to their quantum nature, and in doing so, they continuously define and maintain the energy scales of the universe without a single act of classical measurement. This inherent background fuzziness is not a bug in the system. It is the essential feature that allows the quantum world to be stable and self-consistent, preventing a catastrophic collapse that would otherwise occur under classical rules. This radical shift in perspective from a universe of definite things to a universe of vibrating potentials naturally leads us to an even more astonishing idea. If the most fundamental layer of reality is informational and probabilistic, then perhaps the very notion of volume and size is an illusion emerging from something even more primitive. This brings us to the threshold of the holographic principle, a concept that suggests all the information needed to describe a three-dimensional volume of space might actually be encoded on its two-dimensional boundary. It's a revelation that turns our understanding of dimension and scale inside out, suggesting that the universe's knowledge of itself is not stored within its expanse, but painted on its outermost shell. So if the quantum world shows us that reality is fundamentally fuzzy and probabilistic, then where does that leave our classical notion of a solid, three-dimensional universe with a definite size? It leads us to one of the most mind-bending ideas in all of theoretical physics, the holographic principle. This concept forces us to completely reimagine the nature of reality itself. It proposes that everything we perceive in our three-dimensional world, every galaxy, every planet, every person, every thought, might actually be a projection of information stored on a distant, two-dimensional surface. Think of it like a cosmic credit card hologram. That shimmering, three-dimensional eagle isn't actually floating above the plastic. It's an optical illusion generated by a pattern of ridges and lines etched onto the card's two-dimensional surface. The holographic principle suggests our entire universe might operate on a similar, though infinitely more complex, principle. The richness, depth, and volume we experience could be a magnificent illusion emerging from a flat, data-rich boundary. This astonishing idea didn't come from nowhere. It emerged from the deepest puzzles of black hole physics. In the 1970s, physicist Jacob Bekenstein made a revolutionary proposal. He argued that a black hole's entropy, a measure of its hidden information or disorder, is not proportional to its volume, as one might intuitively guess. Instead, it's proportional to the surface area of its event horizon. This was a staggering insight. Entropy had always been a volumetric property. The more space something occupies, the more ways its internal components can be arranged, and thus the higher its entropy. But Bekenstein was saying that for the most extremely condensed objects in the universe, all that information, all that potential for complexity, was somehow encoded on their surface. Stephen Hawking later confirmed and refined this idea, leading to the famous Bekenstein-Hawking formula. This formula tells us that the maximum amount of information you can stuff into any region of space is not determined by the volume inside, but by the area of the surface that encloses it. Let that sink in for a moment. It means if you have a spherical region of space, the ultimate limit of its information storage isn't related to how much you can cram into its cubic volume, but is instead defined by the square of its radius. It places a hard, physical limit on reality, suggesting that the universe has a finite data density, a maximum number of bits per unit of space, but more importantly, it turns the relationship between information and space completely on its head. In this view, the three-dimensional world inside the sphere isn't the primary reality. It's a projection, a rendering of the information stored on its two-dimensional boundary. The volume is not the source of the information, it is a consequence of it. The universe, therefore, doesn't need to know its size in the traditional sense of measuring a diameter. Instead, its scale is an emergent property that simply falls out of the total amount of information it contains and how that information is processed and displayed. The size is in the data, not in the distance. This transforms our understanding of cosmic scale from a geometric problem into an informational one. The question shifts from how big is the universe to how much information can the universe contain, and on what surface is that information encoded. The three-dimensional expanse we move through becomes a kind of user interface, a convenient and immersive display for the underlying data. The universe knows its own size because that size is literally defined by the information capacity of its outermost shell. There is no separate measurement happening. The data density and the spatial dimensions are two sides of the same coin, locked together by the fundamental laws of physics. This profound connection between information and geometry suggests that the cosmos is, at its most fundamental level, a system of knowledge, and what we perceive as its vast physical size is simply that knowledge made manifest, a holographic projection on a scale so grand we are living inside it. Now, if the holographic principle suggests the universe encodes its information on a boundary, then we must ask, what is the engine that drives this cosmic data processing? The answer lies in a concept so fundamental to our everyday experience that we often take it for granted: the relentless one-way flow of time. This isn't just a psychological sensation. It's a physical property of the universe deeply intertwined with the concept of disorder or entropy. Think of a hot cup of coffee left on a counter. It never spontaneously heats up. It always cools down, its heat dissipating into the room until it reaches the same temperature as its surroundings. This inevitable slide from order to disorder, from a state of concentrated energy to a state of even distribution, is governed by the second law of thermodynamics. It states that the total entropy of a closed system always increases over time. This law gives time its arrow, its irreversible direction from past to future. For the universe as a whole, the ultimate closed system, this means it began in a state of incredibly low entropy and has been sliding towards a state of maximum disorder or heat death ever since. This thermodynamic journey is not separate from the universe's expansion. The two are intimately linked, dancing a cosmic tango where each step defines the other. In the very early universe, moments after the Big Bang, conditions were exquisitely ordered. Matter and energy were packed into an incredibly hot, incredibly dense, and incredibly smooth state. This was a state of profound low entropy, a pristine starting point of immense potential. As the universe expanded and cooled, that potential was unlocked. Gravity began to pull matter into clumps, forming the first tiny irregularities that would eventually become galaxies and stars. This process of structure formation is actually a local increase in order. A galaxy is far more structured than a smooth cloud of gas, but it comes at a cost. The gravitational collapse and nuclear fusion in stars release enormous amounts of radiation and heat, which floods out into the vastness of space. This dissipated energy represents a massive, net increase in the universe's overall entropy. So, the very formation of the complex structures we see today is a side effect of the universe's relentless drive toward greater disorder. The expansion of space provides the stage for this grand thermodynamic play, creating ever more room for energy to spread out and for entropy to increase. This is where the cosmic scale becomes implicitly defined by this thermodynamic clock. The current size of the universe is directly correlated with its current state of entropy. We can look at the universe today, measure its background temperature and the distribution of matter and energy, and get a reading on its total entropy. That number is astronomically large, but we also understand the physics of how it got there from that initial low entropy state. This means that the universe's size isn't just a geometric fact, it's a thermodynamic milestone. It is the direct result of 14 billion years of irreversible processes playing out across an expanding arena. The universe doesn't need to stop and take a measurement of its own diameter. Its scale is continuously updated and reflected in the ever-increasing value of its own entropy. The arrow of time, pointing from a small, ordered past to a vast, disordered present, carves the universe's dimensions into the very history of its evolution. This paints a breathtaking picture of cosmic self-awareness. The initial conditions of the Big Bang provided the universe with a kind of wind-up key, a store of low entropy, of potential for change and complexity. As the key unwinds, as entropy increases, the universe expands, structures form, and time marches forward. The size of the cosmos at any given moment is simply the current reading on this grand thermodynamic clock. The universe knows its scale because it is living its history, and that history is written in the irreversible language of increasing disorder. The vast expanse we see today is not a static stage but a dynamic, evolving testament to a process that began with a perfectly ordered whisper and is evolving toward a perfectly disordered silence, with every moment in between implicitly defining the magnificent scale of the journey itself. But to truly appreciate the universe's calm, expansive middle age, we must journey back to its most turbulent and transformative infancy, a period of almost unimaginable violence and growth known as the Inflationary Epoch. Picture the universe not even a second old, a seething, superheated broth of energy and nascent forces. In these first fleeting moments, the cosmos was a chaotic place, riddled with wild variations in density and temperature. Left to the standard, gradual expansion of the Big Bang, these irregularities would have been magnified, potentially leading to a universe clumped into massive, unbearable knots or torn apart into empty, desolate voids. It would have been a cosmos incapable of forming the delicate, structured beauty we see today. Something extraordinary had to happen to tame this chaos, to set the stage for a universe that could eventually host galaxies, stars, and planets. That something was inflation. This wasn't just a slightly faster version of the expansion we see today. It was a cataclysmic, exponential stretching of spacetime itself, a growth spurt of such ferocious speed that it dwarfs all understanding. In a time span so short it makes a nanosecond seem an eternity, perhaps from around 10 to the power of -36 seconds to 10 to the power of -32 seconds. The universe doubled in size not once or twice, but somewhere between 60 and 100 times over. To grasp this, imagine a single atom suddenly swelling to the size of our entire observable universe, all in the blink of an eye. This wasn't an explosion into space. It was the hyper-accelerated stretching of space, a fundamental repainting of the cosmic canvas on which everything would later be drawn. This incredible event wasn't random or unexplained. The leading theory posits it was driven by the potential energy of a hypothetical field that permeated all of space, known as the inflaton field. Think of this field like a ball resting precariously at the very top of a steep, smooth hill. This high point represents a state of immense, unstable energy. To find stability, the ball must roll down into the valley below. But in the unique conditions of the infant universe, this roll was initially excruciatingly slow, a phenomenon known as a slow roll. And while the ball was perched in that high-energy state at the top of the hill, its incredible potential energy did something remarkable to the fabric of space-time. It generated a powerful repulsive gravity, a kind of anti-gravity that pushed every point of space away from every other point with unbelievable force. This was the engine of inflation. It was this scalar field, this cosmic fuel, that powered the universe's most dramatic growth phase, forcefully smoothing out its wrinkles and calibrating its geometry on a monumental scale. As this inflationary expansion finally ended, the inflaton field reached the bottom of its hill, its immense potential energy decaying into a torrent of particles and radiation that flooded the universe, reheating it and setting the stage for the familiar hot Big Bang nucleosynthesis that would follow. But inflation's most crucial gift was the subtle, quantum-scale signature it imprinted on the cosmos. During that brief but violent stretching, the tiny, random quantum fluctuations that are always fizzing in any field were not smoothed away. Instead, they were magnified and frozen into the very fabric of space-time. A microscopic blip in density here, a minuscule variation in temperature there. These quantum jitters were stretched across astronomical distances, becoming the seeds for all future structure. The pattern of slightly denser regions left behind in the wake of inflation became the gravitational wells that, over billions of years, would pull in matter to form the first galaxies, stars, and ultimately, the vast cosmic web we observe today. This means the grand architecture of the universe, from the largest supercluster to the smallest dwarf galaxy, owes its existence to quantum noise amplified to cosmic proportions during this primordial event. This process did more than just create the seeds for structure. It effectively gave the universe a permanent, built-in sense of scale. The pattern of these amplified fluctuations was imprinted directly onto the cosmic microwave background radiation, the afterglow released when the universe became transparent. When we look at the detailed map of the CMB, we are not just seeing a baby picture of the universe, we are reading a direct fossilized record of the inflationary epoch itself. The specific statistical properties of the hot and cold spots, their size, distribution, and their correlation across the sky are a direct reflection of the physics of inflation, of how fast it happened and how it ended. This pattern acts as a cosmic ruler etched into the sky at the very beginning. The universe doesn't need to measure its current size by looking outward. It can, in a sense, look inward at this imprinted blueprint. The current vast expanse is simply the evolved, gravitationally enhanced version of that initial pattern, its scale predetermined and encoded from the very first moments. Inflation provided the initial calibration, setting the dials for the universe's expansion in such a precise way that the concept of actively measuring its size becomes almost irrelevant. The dimensions were set in stone, or rather, in space-time, during that first furious fraction of a second. But even as we explore the vastness made possible by inflation, we must confront a humbling and profound truth. We are, in a very real sense, prisoners of light and time. The universe may be unimaginably large, perhaps even infinite, but the portion we can ever hope to see or interact with is strictly finite. This isn't a limitation of our technology. It is a fundamental, physical boundary woven into the fabric of causality itself. We live inside a cosmic bubble called the observable universe, and its edge is not a place you could ever travel to. It is a horizon, a limit of knowledge imposed by the relentless, finite speed of light and the relentless expansion of space. Everything we see, from the screen in front of you to the most distant galaxy at the edge of our telescopes, is connected to us by a thread of light that has had just enough time, since the beginning of everything, to reach our eyes. This creates a fascinating and subtle form of cosmic self-awareness. The universe doesn't have a giant ruler to check its own diameter. Instead, its knowable size is defined by a simple, elegant, and unbreakable rule: nothing can travel faster than light. Because of this, every single point in the universe has its own unique observable bubble. For us here on Earth, our horizon is about 46.5 billion light-years in every direction. That sphere contains all the matter and energy with which we can possibly have exchanged a signal since the Big Bang. An alien on a planet 10 billion light-years away would have their own, slightly different bubble, overlapping with ours but also containing regions we can never see, and vice versa. The universe, in its entirety, is partitioned into an uncountable number of these causally connected domains, each one a self-contained island of knowledge within the greater whole. This partitioning isn't a design flaw. It's a fundamental feature of a cosmos governed by relativity. The universe knows its observable scale through the very fact that these horizons exist. They are the direct and inevitable consequence of its age and the rules of its operation. We can break this down even further into two specific, powerful types of horizons that define our cosmic experience. The first is the particle horizon. Think of this as the ultimate boundary of past events. It marks the farthest distance from which light could have possibly reached us since the dawn of time. It is our personal, ultimate lookout point into the past. Everything within our particle horizon is, in principle, visible to us, though the light from its most distant edges is incredibly faint and stretched, showing us the universe in its swaddling clothes. The second is the event horizon, a concept that becomes crucial due to the accelerating expansion driven by dark energy. This is not the same as a black hole's event horizon, though the principle is similar. The cosmological event horizon defines a boundary for future events. It marks the farthest distance from which a light signal sent today could ever possibly reach us in the future. Because the space between distant galaxies is stretching faster than light can traverse it, there are galaxies whose light is reaching us now, but if they turned off their lights today, we would never know. They have already passed beyond our event horizon and are, for all future eternity, causally disconnected from us. Their future and our future will never again interact. This creates a startlingly introspective view of the cosmos. The universe isn't a single, unified entity where every part can eventually communicate with every other part. It is a collection of domains that are forever drifting out of each other's reach, islands of awareness slowly losing touch in an ever-expanding ocean. This self-imposed isolation is not a flaw but a profound expression of the universe's internal logic. The existence of these horizons is a direct readout of its expansion history and its fundamental constants. By simply operating according to the rules of general relativity and quantum mechanics, the universe naturally and continuously defines the scale of what is knowable from every single point within it. The size of the observable bubble isn't a measured quantity. It is a dynamic, evolving property that is baked into the relationship between the age of the universe, the speed of light, and the rate of expansion. This elegant, self-referential system sets the stage for the next great actor in our cosmic drama, a mysterious force that is actively reshaping these horizons and dictating the ultimate fate of all these isolated islands of light. But if the cosmological event horizon defines the boundaries of what we can ever know, then what mysterious force is actively pushing those boundaries further away, accelerating the expansion of space itself and sealing the fate of distant galaxies to eternal isolation? This brings us to the single greatest puzzle in modern cosmology, a phenomenon so strange it seems to defy intuition: dark energy. For most of the 20th century, astronomers believed the universe's expansion was slowing down. It made perfect sense. After the initial thrust of the Big Bang, the relentless pull of gravity from all the matter in the cosmos should have been acting like a cosmic brake, gradually decelerating the outward rush of galaxies. The only question was whether there was enough matter to eventually halt the expansion entirely and pull everything back in a big crunch, or if the universe would just keep coasting onward forever, slowing to a crawl but never stopping. Then, in the late 1990s, two independent teams made a shocking discovery. By carefully measuring the distance to extremely far-off supernova exploding stars that serve as standard candles, they found something utterly unexpected. These distant stellar explosions were fainter than they should have been if the expansion were slowing down. The only possible explanation was that the expansion of the universe wasn't decelerating at all. It was speeding up, some unknown repulsive force counteracting gravity on the largest scales was pushing galaxies apart faster and faster. This discovery was so revolutionary it earned the researchers the Nobel Prize and forced a complete rewrite of our cosmic story. This mysterious repulsive force was dubbed dark energy, and its nature remains one of the most profound enigmas in physics. What makes it so peculiar and so crucial to the universe's self-knowledge of its scale is its bizarre behavior. Think about ordinary matter and radiation. As the universe expands, the volume of space increases. The number of atoms and photons stays roughly the same, so they get more spread out. This means their energy density, the amount of energy per cubic centimeter of space, decreases over time. Their gravitational influence, which is attractive, weakens as the cosmos grows. Dark energy is the complete opposite. Its energy density appears to be constant. It does not dilute as the universe expands. Imagine a strange, ethereal fluid that fills all of space. As the universe grows, creating new volume, this fluid doesn't thin out. Instead, more of it just seems to appear, maintaining the same fixed density everywhere forever. This simple property has a staggering consequence. In the early, dense universe, matter and radiation were king. Their gravity dominated, slowing the expansion and pulling structures together. But as eons passed and the cosmos became more and more vast, matter and radiation diluted away, their influence waning. Dark energy's influence, however, held steady. And at a certain point in cosmic history, about 5 billion years ago, its constant repulsive push finally overcame the weakening pull of gravity. The expansion of the universe crossed a threshold and began to accelerate. This wasn't a one-time event, it's an ongoing process. As space continues to grow, dark energy's dominance only increases, ensuring the acceleration will continue forever, fundamentally guiding the future scale and fate of everything. The leading candidate for this strange energy is something Einstein himself stumbled upon, though he later called it his greatest blunder, the cosmological constant. When he was first developing his theory of general relativity, the prevailing scientific belief was that the universe was static and eternal. It didn't expand or contract. Einstein found that his equations naturally described a dynamic universe that would either collapse under its own gravity or fly apart. To force his theory to match the supposed static reality, he introduced an extra term into the equations, represented by the Greek letter lambda. This term represented a repulsive force that would perfectly balance the attractive force of gravity on the largest scales, creating a static, stable cosmos. Years later, when Edwin Hubble discovered the universe was indeed expanding, Einstein discarded the cosmological constant as an unnecessary fudge. But with the discovery of acceleration, it made a triumphant return. In modern theory, lambda is no longer a fudge factor but a fundamental part of reality. It represents the energy inherent to the vacuum of space itself. This vacuum energy, according to quantum physics, should be teeming with virtual particles flickering in and out of existence. The cosmological constant is the simplest way to describe this energy's repulsive gravitational effect. It suggests the universe has a built-in tendency to expand, a default setting woven into the empty void that only becomes apparent once the universe grows large and sparse enough for it to shine through. This changes everything about how we view the cosmos's self-awareness. The universe isn't just expanding, it's accelerating according to a precise, pre-programmed rule written into its fundamental laws. The value of the cosmological constant acts as a cosmic throttle, setting the rate of acceleration. This means the universe's future size isn't a vague, open-ended question. It is being actively and continuously defined by this relentless pressure. The cosmos is, in a very real sense, calibrating its own scale in real time through the dynamic balance between the attractive force of matter and the repulsive force of dark energy. As matter dilutes and dark energy's influence grows, that balance shifts, and the universe responds by increasing its expansion rate accordingly. It's a perfect, automated feedback system. There is no central calculator determining the correct size. The size is the output of the equation itself. The universe is always aware of its current dimensions because those dimensions are the direct and inevitable result of the forces playing out within it. Dark energy ensures that this self-knowledge isn't static. It's an evolving understanding, a constant update to the cosmic ledger that dictates an ever larger, ever more isolated future for the islands of matter within the growing void. Yet for all its silent, mathematical elegance, this accelerating expansion is only half the story of the cosmos. To truly grasp how the universe understands its own dimensions, we must shift our gaze from the empty, stretching void to the brilliant, dense islands of light and matter that dot the darkness. If dark energy is the force pushing the stage apart, then galaxies are the actors upon it, and their arrangement is not a random scattering but a deeply meaningful pattern, a kind of cosmic fingerprint left over from the universe's earliest moments. When we look up at the night sky, we're not just seeing points of light, we're witnessing the grand, evolved architecture of reality, a structure that passively and perfectly records the scale of the cosmos without a single act of measurement. This architecture is known as the cosmic web, and it is one of the most breathtakingly beautiful and complex structures in all of nature. It's a vast, interconnected network of galaxies, woven together like the filaments of a spider's web, with immense, empty voids stretching between them. These filaments can be hundreds of millions of light-years long, connecting dense knots where thousands of galaxies swarm together in massive clusters. This isn't a static sculpture, it's a dynamic, evolving entity with galaxies flowing along these filamentary highways like cars on a cosmic freeway, drawn by the relentless pull of gravity towards the densest intersections. The pattern is eerily familiar, mirroring the structure of a biological neural network or the frothy bubbles in a sink of dishwater, a testament to how universal the underlying physics of structure formation truly are. The crucial point is that this magnificent web did not form by chance. It is the direct, grown-up version of those tiny, quantum density fluctuations that were amplified during the inflationary epoch and then frozen into the hot plasma of the early universe. Think of it like a sound wave echoing through the cosmos. In the first few 100,000 years, the universe was so hot and dense that matter and light were locked in a constant tug of war, creating regions of slightly higher and lower pressure, actual acoustic waves traveling through the primordial soup. When the universe finally cooled enough for atoms to form and light to travel free, that pattern of waves was imprinted onto the cosmic microwave background. Those faint ripples of hot and cold were the blueprints. Over billions of years, gravity got to work. Every slightly denser region had a tiny bit more gravitational pull. It attracted more matter from its surroundings, growing denser and denser, while the less dense regions were stripped bare, evolving into the great voids. The web we see today is simply the final, gravitationally enhanced result of that process. The universe didn't need an architect to design this web. It grew it organically from its own initial conditions, following the simple, immutable law of gravity. This is where the concept of scale becomes inherent, not measured. Astronomers have a powerful tool to quantify this large-scale structure called the two-point correlation function. In simple terms, this measures the probability of finding two galaxies at a certain separation compared to what you would expect if they were just randomly scattered across the sky. And what they find is a very specific, non-random pattern. Galaxies are much more likely to be found about 500 million light-years apart than they are to be either much closer or much farther. This preferred scale isn't an accident, it's a fossil. It's a direct echo of the size of those primordial sound waves at the moment the universe became transparent, a scale known as the sound horizon. That specific distance was set by the speed of sound in the early plasma and the age of the universe at that time. It acts as a standard ruler etched into the very distribution of matter. So, when we measure the correlation function of galaxies today and find that they prefer to be separated by a certain distance, we are not imposing a measurement on the cosmos. We are reading a measurement that the universe made of itself 14 billion years ago and then baked into all subsequent structure. The large-scale structure is a passive data storage device, a cosmic hard drive that maintains a record of its own initial conditions and therefore its own inherent scale. This transforms our understanding of the cosmos from a collection of objects to a unified, intelligent system. The arrangement of galaxies is not something the universe has to go out and check. It is the living, breathing result of its own history and its own laws. The pattern is the information. The voids are not empty nothingness. They are a crucial part of the pattern, defining the negative space that gives the filaments their form. The universe knows its scale because that scale is woven into the gravitational tapestry of the cosmic web, a permanent, evolving monument to its own origin and size, standing as proof that the cosmos understands itself through the beautiful, inevitable consequences of its own existence. So if the cosmic web is the universe's grand, evolved architecture, then how do we, as tiny observers within it, possibly hope to map its staggering scale and read the story written into its patterns? We don't send out giant intergalactic surveying teams. Instead, we undertake a monumental feat of cosmic cartography, using the light from distant galaxies themselves as our guide. This is the realm of redshift surveys, a breathtakingly ambitious branch of astronomy that doesn't just look at the sky, but listens to its deepest histories, transforming the faint whispers of ancient starlight into a precise three-dimensional atlas of the cosmos. These projects are not about actively measuring the universe with some external tool. They are about creating a detailed portrait of how the universe has measured itself through its own expansion, a self-portrait painted in the subtle shifts of color from billions of receding suns. The most famous of these endeavors is the Sloan Digital Sky Survey, a project that represents one of the most data-rich and transformative scientific experiments in human history. For over 2 decades, using a dedicated telescope in New Mexico, the SDSS has methodically scanned vast swaths of the heavens, not to take pretty pictures, but to capture the spectra of millions upon millions of celestial objects. A spectrum is like a cosmic barcode. By passing a galaxy's light through a prism, astronomers can break it down into its constituent colors. Embedded in that rainbow are dark absorption lines, specific fingerprints left by elements like hydrogen and calcium in the galaxy's stars. Here's the magical part: because the universe is expanding, the light from a galaxy moving away from us is stretched. This stretching shifts the entire spectrum, including all those barcode lines, toward the redder, longer wavelength end of the spectrum. The faster the galaxy is receding, the greater this redshift. It's a direct physical consequence of the expansion of space itself, a perfect built-in speedometer. By measuring the precise amount of this redshift for each galaxy, astronomers can calculate its velocity away from us, and thanks to the Hubble-Lemaitre law, that velocity directly correlates to its distance. One measurement of a color shift gives you both speed and distance. It's an incredible cosmic cheat code. The result of this painstaking work is not just a list of numbers, it is a revolutionary three-dimensional map of the local universe. When you plot the positions of these millions of galaxies using their calculated distances, the faint two-dimensional sprinkling of stars on the night sky suddenly explodes into depth and structure. You see the cosmic web in all its glory, the vast, empty voids, the delicate, filamentary bridges, and the massive, dense clusters where thousands of galaxies swarm together. This map is a historical record. Because light takes time to reach us, the galaxies at the farthest edges of this map are also the ones we are seeing from the deepest past. The survey is a kind of time machine, allowing us to see how the large-scale structure of the universe has evolved over billions of years. We can watch the cosmic web slowly assemble itself as gravity pulls more and more matter into the filaments and nodes. The universe isn't holding still for its portrait. It is actively showing us the movie of its own growth, with the redshift of each galaxy providing the timestamp for its scene. But the true power of these maps goes far beyond just creating a beautiful visualization. Hidden within the statistical distribution of all these galaxies, the precise distances between them, lies a ghostly echo from the dawn of time, a fossilized sound wave that serves as the universe's own preferred standard ruler. This fossil is known as a Barrian acoustic oscillation. To understand it, we have to journey back to the universe's first 400,000 years. At that time, the cosmos was a seething, opaque plasma, a hot soup of protons, neutrons, and electrons, all constantly buffeted by photons of light. In this dense medium, gravity tried to pull the matter together into clumps, while the intense radiation pressure from the photons tried to push it apart. This tug-of-war created powerful spherical sound waves or pressure waves that rippled outward through the primordial plasma. Imagine dropping a pebble into a pond. These were the universe's first and largest ripples. Then, in a flash, everything changed. The universe expanded and cooled enough for atoms to form, suddenly allowing photons to travel freely. This moment of decoupling, which released the cosmic microwave background, also froze the sound waves in their tracks. Each wave was caught mid-ripple, leaving a spherical shell of matter that had been pushed outward by the pressure wave, a shell with a slightly higher density of protons and neutrons, or baryons. This specific distance, the distance that sound could travel in the plasma before the universe became transparent, became a permanent ruler stamped onto the fabric of the cosmos. That distance is about 500 million light-years. For the next 13 billion years, as the universe expanded, this standard ruler expanded with it. Gravity continued to pull matter into the overdense regions, including the fossil shells left by those sound waves, to form the galaxies we see today. So, when we look at a modern 3D map from a redshift survey, we see that galaxies have a slight preference to be separated by this specific, scaled-up distance. It manifests as a small but statistically significant excess in the number of galaxy pairs that are roughly 500 million light-years apart. This isn't a subtle effect. It's a clear peak in the data, a ringing signal in the cosmic web. This is the universe revealing its scale in the most elegant way possible. Astronomers don't need to know the physical size of anything. They simply measure this statistically preferred separation between galaxies in the redshift map. They know that this observed angular size on the sky corresponds to a true physical size that was set by the physics of the early universe. It's like finding a ruler of unknown length, but knowing that the distance between the inch marks is always exactly 1 inch. By seeing how small that ruler appears to us from our vantage point, how closely packed those inch marks seem, we can calculate its actual distance from us. The Barrian acoustic oscillation peak is our cosmic inch mark. By measuring its apparent size in our sky and comparing it to its known, predicted physical size, we can precisely determine the distance to the galaxies in that part of the map, and by extension, measure the expansion history of the universe itself. The universe provided the ruler at the beginning of time, and redshift surveys are simply the tool we use to read it, allowing us to see the cosmos not as a silent void, but as a resonant chamber still vibrating with the echoes of its own creation. But this breathtaking precision, this cosmic architecture that allows us to even exist to observe it, leads us to a profound and almost unsettling question. Why is the universe so perfectly set up for life, with all the possible values the constants could have taken, and all the possible sizes the cosmos could have been? The odds of landing on a combination that allows for stars, planets, and conscious beings seem astronomically small. It feels less like a random accident and more like the universe was rigged from the start in our favor. This is the heart of the anthropic principle, an idea that bridges the gap between physics and philosophy, suggesting that the universe's scale and laws are not arbitrary but are, in a very real sense, necessary. The very fact that we are here to ponder the question imposes a strict selection effect on what kind of universe we can possibly find ourselves in. We can think of it like a cosmic lottery with an almost infinite number of losing tickets. Imagine a universe where the strength of gravity was just a fraction stronger. In such a cosmos, the gravitational pull would be so intense that any star that formed would burn through its fuel at a ferocious rate, collapsing into a black hole after only a brief, violent existence. There would be no long-lived, stable suns to nurture planets for billions of years. Conversely, if gravity were slightly weaker, matter would never have been able to clump together effectively after the Big Bang. The primordial gas would have simply drifted apart into a thin, ever-expanding haze, never condensing into the first galaxies and stars. The same razor's edge applies to the universe's size and expansion rate. A universe that collapsed too quickly in a big crunch would never give life a chance to evolve. A universe that expanded too rapidly would see matter diluted into nothingness before gravity could even begin its work of building structure. Our universe, with its specific size and its specific constants, seems to have hit the jackpot. It's Goldilocks on a cosmic scale, not too hot, not too cold, not too big, not too small, but just right. This isn't just about us. The principle suggests that the universe's ability to generate complexity from swirling galaxies to swirling thoughts is an inherent property of its parameters. The size is integral because it is directly tied to its age and its expansion history. A universe that is too small wouldn't be old enough for generations of stars to have lived and died, forging the heavy elements like carbon and oxygen that are the building blocks of life as we know it. The scale of the cosmos, the sheer amount of time and space it provides, is a prerequisite for the long, slow, intricate dance of cosmic evolution. The universe doesn't need to be conscious of this fact. Its self-consistency is built in. The laws that govern the formation of a hydrogen atom are the same laws, scaled up through gravity and time, that govern the formation of a supercluster of galaxies. The system is closed and self-referential. Its ability to sustain complexity is a direct output of its initial conditions and fundamental settings. In this view, the universe knows its size because that size is a critical variable in the equation of its own existence and its potential to become more than just a featureless void. This line of thinking inevitably pushes us toward a staggering possibility. If the conditions for life are so incredibly specific and unlikely, then perhaps our universe isn't the only one. Maybe we are just one outcome in a vast, perhaps infinite, ensemble of universes, a multiverse. In this breathtaking scenario, each universe could be a separate bubble with its own unique set of physical laws and constants. Some might collapse instantly, Others might expand into cold, empty darkness. Most would be stillborn, incapable of generating even a single atom. But in a few rare cases, by pure statistical chance, the numbers would line up perfectly. In those universes, the conditions would be just right for galaxies to form, for stars to shine, and for beings to eventually look up at their night sky and wonder at their own improbable existence. The anthropic principle in this context becomes a form of cosmic natural selection. We shouldn't be surprised to find ourselves in a universe that is finely tuned for life, because we couldn't possibly find ourselves anywhere else. Our presence here is the ultimate selection bias, filtering out all the universes where life was impossible. The multiverse idea doesn't explain why our universe has the rules it does. It simply embeds our specific, life-friendly cosmos within a much vaster and more exotic landscape where every possible rulebook is written somewhere, making the concept of a single, correct universe size completely relative. But the staggering fine-tuning we see in our own universe, the seemingly perfect calibration of constants and scale that allows for our existence, pushes our imagination toward an even more radical possibility. What if our cosmos, with its specific dimensions and laws, isn't the only one? What if it is merely a single bubble in a frothing, infinite ocean of realities, each with its own unique physics and its own definition of what size even means? This is the realm of multiverse theory, a concept that doesn't just expand the universe but explodes the very idea of a singular reality, transforming the question of cosmic self-knowledge from a solitary puzzle into a collective property of a vaster, more mysterious meta-reality. In this breathtaking framework, our home universe loses its privileged status. It's approximately 93 billion light-year diameter, and its specific values for the speed of light or the strength of gravity are no longer fundamental, universal truths. They are simply local bylaws, the particular settings that happen to freeze in place within our cosmic bubble. Beyond our event horizon, inaccessible and forever separate, could be an infinite number of other universes, each born from its own inflationary seed or quantum fluctuation in a greater metacosmos. In sum, the cosmological constant might be vastly stronger, causing space to rip apart in a violent, big rip before the first atoms could even form. In others, gravity might be so weak that no stars ever ignite, leaving a permanent, dark, and diffuse haze of elementary particles. There could be universes that are microscopic, blinking in and out of existence in a fraction of a second, and others so immeasurably vast that our entire observable cosmos would be smaller than a single quark within it. Size in this grand ensemble becomes a variable, not a constant. A universe doesn't know its size in any absolute sense. It simply is a certain size, one possibility in a near-infinite distribution of outcomes. Its scale is a contingent fact, a roll of the cosmic dice at the moment of its genesis, rather than a necessary property written into the bedrock of all existence. This shift in perspective is powerfully supported by the leading theories of fundamental physics, particularly inflationary cosmology and string theory. The same inflationary mechanism that so elegantly explains the smoothness and structure of our own universe also naturally predicts the eternal creation of a multiverse. In the eternal inflation scenario, the inflattened field doesn't settle into its lowest energy state everywhere at once. Think of it like a vast mountain landscape where our universe is one valley. The process of inflation can keep occurring on the mountain slopes, creating ever-new regions of rapidly expanding space-time that eventually settle into their own stable valleys, their own distinct universes with different properties. Each of these bubble universes nucleates with its own random set of initial conditions, which then determine its subsequent expansion history, its ultimate size, and the physical laws that emerge within it. Our universe's scale is therefore not preordained. It's the result of a random quantum fluctuation during this eternal inflationary process, one outcome in an endless cosmic lottery. String theory, our most ambitious attempt to unify gravity with quantum mechanics, adds another layer of incredible depth to this idea. It proposes that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. For the math of string theory to work, it requires more than the 3 spatial dimensions we experience. It needs 10 or 11. The theory explains our perception of a 3-dimensional world by suggesting that the extra dimensions are compactified, or curled up into shapes too small for us to perceive. And here's the crucial part: there is not just one way to curl up these extra dimensions. The geometry of this compactification, the specific shape and size of these hidden dimensions, determines the effective laws of physics in the observable, 3-dimensional universe that results. Things like the electron's mass, the number of particle families, and crucially, the strength of the fundamental forces, all depend on the geometry of this hidden landscape. String theory allows for a colossal number of possible solutions, perhaps 10 to the 500 or more, each corresponding to a different universe with different physical constants. This is the famous string theory landscape, a vast, abstract terrain of possibilities where each point represents a unique universe with its own unique properties, including its own definition of scale. The size of our observable cosmos is thus intimately tied to the specific, randomly determined way our extra dimensions curled up at the dawn of time, making our reality just one garden in a landscape of bewildering diversity. Within this multiversal framework, the very act of measurement takes on a completely different, almost philosophical meaning. If our universe is just one among countless others, then asking why it is the size it is becomes akin to asking why a particular grain of sand on a beach is the exact size that it is. There is no deeper reason. It's simply the outcome of a random process with a distribution of results. The concept of the universe knowing its own size becomes almost trivial. It doesn't need to know. Its scale is an accidental, emergent property of its particular birth circumstances within a wider meta-reality. There is no absolute ruler against which to measure, because every universe in the ensemble has its own internal rulers, its own constants, its own definition of a meter or a light year based on its local laws. Measurement is only relevant and consistent within a given universe. It has no meaning across the multiverse. This perspective doesn't diminish the profound self-consistency we see within our own cosmos. Instead, it embeds that self-consistency within a much larger, more complex and potentially chaotic system where our orderly reality is a special, life-friendly exception rather than the rule. The search for a fundamental reason for our universe's specific scale may be a quest that only makes sense from our limited, internal viewpoint, a local question without a global answer. But if the multiverse suggests that size is a local and accidental property, then how can we even begin to describe or understand the specific, self-consistent scale of our own universe with such breathtaking precision? The answer lies not in any physical instrument, but in a realm of pure abstraction that seems to underpin reality itself, the immutable language of mathematics. We often think of math as a human invention, a tool we created to count objects and measure fields. But an increasingly compelling perspective, one echoed by great thinkers from Pythagoras to Einstein, is that mathematics is not something we invented, but something we discovered. It is the native tongue of the cosmos, the fundamental code in which the laws of physics are written. The universe doesn't run on math like a computer runs on software. It is math in a very literal sense. Its behavior, its structure, and crucially, its sense of scale are all expressions of mathematical relationships that exist independently of any conscious mind trying to solve them. This becomes astonishingly clear when we look at the equations that govern reality, from the cosmic curvature of general relativity to the probabilistic dance of quantum field theory. These aren't just models that approximate what we see, they are breathtakingly precise descriptions of how things actually work, and within these equations we find a powerful clue to how the universe handles scale. They are filled with what physicists call dimensionless constants. These are pure numbers, ratios that have no units like meters or seconds attached to them. They are relationships, not absolutes. The most famous example is the fine structure constant we encountered earlier, approximately 1/137th. This number defines the strength of the electromagnetic force. It doesn't matter if you're measuring an atom in a lab on Earth or in a galaxy a billion light-years away, this ratio is the same. The universe, through this constant, defines the force not by some absolute strength, but by its relationship to other fundamental quantities like the charge of the electron and the speed of light. Size becomes relative, locked into a web of perfect, unchanging proportions. This reliance on ratios extends to the very fabric of physical law, a concept known as scale invariance. Imagine taking a photograph of a physical system and then zooming in or out. If the system is scale invariant, the new picture will look statistically identical to the old one. You won't be able to tell what the magnification is. Many fundamental processes in the universe exhibit this property. The classic example is the ratio of the strength of the electromagnetic force to the gravitational force between two electrons. This number is astronomically large, about 10 to the power of 42. But the key point is that this immense ratio remains constant everywhere in the universe and across time. Gravity is always this unimaginably weaker than electromagnetism. This fixed relationship is why atoms can exist. The electromagnetic force is strong enough to hold electrons in orbit around a nucleus, while gravity is so weak at that scale that it's completely irrelevant. If this ratio were different, atomic structure would fail and chemistry would be impossible. The universe doesn't define an absolute strength for each force separately. It defines the relationship between them. This ensures that the laws of physics work the same way regardless of the scale you're looking at, from the subatomic quantum world to the planetary and stellar systems governed by gravity. The cosmos maintains its self-consistency not by enforcing a fixed size, but by locking all its fundamental parameters into a delicate and perfect dance of ratios. This profound mathematical harmony naturally guides us toward one of the most beautiful and powerful concepts in all of physics, the deep connection between symmetry and the conservation laws that seem to protect the very fabric of reality. It's a relationship that reveals how the universe's self-knowledge of its own properties, including its scale, is woven into the immutable geometry of existence itself. This profound mathematical harmony, this reliance on pure ratios and unchanging relationships, points us toward one of the most elegant and powerful ideas in all of physics: the deep, hidden connection between the beautiful symmetries we observe and the fundamental conservation laws that seem to protect the very fabric of reality. It's a relationship that reveals how the universe's self-knowledge of its own properties, including its scale, is woven directly into the immutable geometry of existence itself, governed by principles that require no external validation. Let's start with symmetry, a concept far richer than mere mirror images or balanced shapes. In physics, a symmetry is a transformation that leaves a system fundamentally unchanged, a kind of invulnerability to change. The most intuitive example is rotational symmetry. The laws of physics don't care which way you're facing. If you perform an experiment in a laboratory and then carefully rotate the entire lab, the outcome will be exactly the same. The universe has no preferred direction. This is rotational invariance. Similarly, there is translational symmetry. The laws of physics are the same here as they are a million light years away. The universe has no special central location. This homogeneity of space, the idea that one patch of vacuum is just as good as any other, is a profound symmetry that implicitly defines a consistent scale. There is no cosmic center from which the rules change. The playing field is uniform, which means the rules of the game themselves define the size and shape of that field. Then there are the more abstract but equally crucial gauge symmetries, which govern the fundamental forces. These are like internal, hidden rotations that ensure the equations for electromagnetism or the strong nuclear force remain consistent and self-contained. Together, these symmetries form the invisible scaffolding of reality, a rigid framework that ensures consistency across the entire cosmos. The true magic, the breathtaking link that connects this abstract geometry to tangible, measurable quantities, was discovered by the mathematician Emmy Noether. In one of the most profound theorems ever formulated, Noether proved that for every continuous symmetry in nature, there is a corresponding conservation law, a quantity that remains constant and cannot be created or destroyed. It's a one-to-one mapping between the geometry of the universe and the physics we observe. The symmetry of translational invariance, the fact that the laws of physics are the same everywhere, directly implies the conservation of momentum. Why is momentum conserved? Because space is homogeneous, no location is special, so there's no reason for the total momentum of a closed system to change. The symmetry of time translation invariance, the fact that the laws of physics are the same today as they were yesterday and will be tomorrow, implies the conservation of energy. Why is energy conserved? Because time is uniform, no moment is privileged, so the total energy in a system must remain constant. This is where the concept of scale becomes deeply embedded. These conservation laws are absolute. They hold true across the entire observable universe, from the collision of quarks to the merger of galaxies. The fact that energy is always conserved is a statement about the large-scale homogeneity of time, a property of the cosmos that inherently references its vast, consistent expanse. The universe doesn't need a meter stick. It has these inviolable principles that act as its eternal, internal regulators. We can see this majestic self-consistency written across the sky in the most ancient light we can detect. The cosmic microwave background radiation is not just a fossil, it is a direct test of the universe's symmetry. When we map its temperature across the entire celestial sphere, we find it is isotropic to an astonishing degree of precision. It is the same in every direction to within tiny 1 part in 100,000 variations. This isotropy is a direct observation of the rotational symmetry of the universe on the largest scales. It tells us that the cosmos has no preferred axis, no cosmic North Star towards which the fundamental laws point. This large-scale uniformity is the observational proof of the homogeneity that Noether's theorem relies upon. It means that the conservation laws we derive in our labs on Earth are not local bylaws. They are the constitution for the entire cosmos. The universe knows it is uniform and isotropic, and this knowledge is expressed through the unwavering conservation of energy, momentum, and angular momentum everywhere we look. Its scale is defined by this very uniformity. The fact that these rules hold true across billions of light years is a direct consequence of its symmetric, self-similar nature. The cosmos understands its own vastness because that vastness is a necessary condition for the very physical laws that allow it to exist in a stable, predictable form. A perfect closed loop of cause and effect where the geometry of the whole guarantees the physics of the parts, and the physics of the parts reflects the geometry of the whole. Now consider the most extreme gravitational environment imaginable, a place where the universe's ability to define its own dimensions reaches a kind of terrifying perfection. A black hole doesn't just participate in this cosmic self-knowledge, it embodies it with an absolute, silent finality. There is no instrument inside a black hole taking measurements. There is no internal clock counting seconds. There is only mass, and from that mass alone, an event horizon emerges with a size precisely dictated by one of the most elegant formulas in all of physics, the Schwarzschild radius. This radius isn't a suggestion or an approximation. It is a fundamental property, an unbreakable law. Double the mass, and you double the radius of the horizon. It is a direct, linear relationship written into the geometry of spacetime by Einstein's field equations. The black hole doesn't calculate this size. Its very existence is a statement of it. Its gravitational influence, the way it warps the space around it, is its size. This is the ultimate example of self-referential geometry, where an object's most basic property, how much space it takes up, is determined not by its volume but by its gravitational signature, a signature that is itself a product of its mass. This profound connection deepens even further when we introduce one of the most startling discoveries in theoretical physics, Hawking radiation. In the 1970s, Stephen Hawking proposed that black holes are not completely black. Due to weird quantum effects happening just outside the event horizon, they should slowly emit a faint glow of particles, effectively causing them to evaporate over astronomical timescales. This revelation tied the black hole's properties together in a breathtaking feedback loop. The temperature of this Hawking radiation is inversely related to the black hole's mass. A supermassive black hole with the mass of millions of suns has a temperature barely above absolute zero, emitting a negligible trickle of radiation. A small black hole, however, would be incredibly hot, radiating away its energy furiously. But here's the crucial part: as the black hole radiates, it loses mass. As it loses mass, according to the Schwarzschild formula, its event horizon must shrink, and as its horizon shrinks, its temperature increases, causing it to radiate even faster. This creates a perfect, self-regulating cycle where the black hole's size, mass, and temperature are locked in a dance that leads to its eventual evaporation. The system is entirely self-contained. It requires no external input or measurement to maintain this consistency. The black hole's properties are in a constant, dynamic conversation with each other, a closed loop of cause and effect that defines its scale from birth to death. This isn't just a curious fact about exotic objects. It's a profound clue about how information and scale are intertwined in the universe. The work of Jacob Bekenstein and Stephen Hawking showed that a black hole's entropy, a measure of its information content, is proportional to the surface area of its event horizon, not its volume. This was a revolutionary idea that hints at a holographic principle for the universe, where all the information needed to describe a three-dimensional volume might be encoded on its two-dimensional boundary. For a black hole, this means its size, as defined by its horizon area, directly tells us about its maximum information capacity. The universe, through the simple, grim physics of gravitational collapse, has created objects that are natural information processors, with their size serving as the ultimate ledger for the data they contain. A black hole doesn't store information about its size is the information. This incredible self-containment naturally makes us wonder, is there a smallest possible size, a fundamental unit of length built into the universe's operating system that even a black hole cannot defy. This leads us directly to the concept of Planck units, a set of measurements derived not from human anatomy or arbitrary standards, but from the fundamental constants of nature themselves. These units represent the scales at which our current theories of gravity and quantum mechanics collide and break down, the point where the very concepts of space and time as we know them cease to have meaning. The Planck length is an almost unimaginably tiny distance, about 10 to the negative 35 meters. To call it small is a monumental understatement. A single proton is about 100 million trillion times larger than the Planck length. This isn't just a number, it's a fundamental limit. It is the scale at which the quantum fluctuations of spacetime itself are so violent that the notion of a smooth, continuous geometry dissolves into a probabilistic foam. This has a direct and stunning implication for black holes and the universe's sense of scale. As a black hole evaporates through Hawking radiation, it gets smaller and hotter, eventually reaching a point where its size approaches the Planck length. At this scale, our current understanding of physics completely fails. We cannot say with any confidence what happens next. Does it vanish in a final burst of energy? Does it leave behind a stable Planck-sized remnant? This fundamental limit suggests that the universe does indeed have a natural, built-in measuring system. The Planck units derived from the gravitational constant, Planck's constant, and the speed of light are the universe's own native system of measurement. They are the rulers against which all other scales are ultimately compared. A black hole's evolution is a journey measured in these natural units, from a macroscopic object defined by its mass to a quantum entity defined by the fundamental limits of reality. In this way, black holes are not just passive examples of self-measurement. They are active explorers of the universe's extreme scales, demonstrating through their life cycle that size is not an arbitrary human concept but an intrinsic property that emerges from the deepest laws of physics, all the way down to the very foam of spacetime. But if black holes represent the universe's most dramatic and self-contained expression of scale, then where does this profound sense of measurement actually begin? To find the answer, we must venture to the very limits of reality itself, to a realm so small that our conventional ideas of space and distance cease to have any meaning. This is the domain of Planck units, a set of measurements that are not based on human constructs like the meter or the second, but are derived directly from the fundamental constants that govern the cosmos. These are the universe's own native, built-in rulers and clocks, providing an absolute benchmark against which all other scales are ultimately compared, a system of measurement that is woven into the very source code of physics. To construct these units, we start with the universe's most basic ingredients, the gravitational constant, big G, which sets the strength of gravity, Planck's constant, which defines the quantum of action and the granularity of the quantum realm, and the speed of light, the ultimate cosmic speed limit that stitches space and time together. By combining these three fundamental constants in just the right way, we can derive natural units of length, time, mass, and even temperature. The Planck length, for example, is an almost inconceivably tiny distance, roughly 10 to the negative 35 meters. To say an atom is vast compared to this is a laughable understatement. Even a single proton is about 100 million trillion times larger. The Planck time, the time it takes for light to travel one Planck length, is an equally mind-numbing 10 to the negative 43 seconds, a duration so short that it is to 1 second what 1 second is to hundreds of trillions of times the current age of the universe. The sheer extremity of these numbers might make them seem like a mathematical curiosity, but they represent something far more profound. the ultimate frontier of known physics. The Planck scale is the point where our two most successful but fundamentally incompatible theories, the smooth, geometric certainty of general relativity and the fuzzy, probabilistic uncertainty of quantum mechanics, are forced to collide. At distances shorter than the Planck length, the Heisenberg uncertainty principle tells us that the energy fluctuations in the vacuum would be so violent that they would create microscopic black holes popping in and out of existence. The very concepts of a smooth, continuous spacetime geometry, of a clear here and there, completely break down. It is believed that at this scale, spacetime itself ceases to be a smooth continuum and becomes a seething, probabilistic foam, a chaotic soup of quantum fluctuations where topology itself might be constantly changing. This isn't just a smaller scale, it is the basement level of reality, the fundamental pixel size of the universe. This is the crucial insight. The universe doesn't use the Planck scale, it is built upon it. These units represent the natural limits of its own operational parameters. When a physicist writes an equation in quantum field theory or general relativity, the Planck units are the natural language that often simplifies the math, stripping away the arbitrary human choices of kilograms and meters to reveal the pure, dimensionless relationships that truly govern behavior. The cosmos operates with an inherent sense of scale because these fundamental limits are baked into the constants that define it. There is no need for an external measurement because the properties of empty space itself, the behavior of quantum fields, and the nature of gravity all conspire to define these absolute benchmarks. The Planck length is not something the universe measures, it is the fundamental resolution of its display. The Planck time is not a duration it counts, it is the tick of its most basic processor. In this system, size and duration are not abstract concepts to be determined, but are intrinsic properties that emerge directly from the immutable laws of existence, providing a perfect, self-referential framework that makes the very idea of an external measuring stick completely superfluous. But this profound connection between a black hole's life cycle and the Planck scale reveals a deeper truth about the cosmos itself. The universe doesn't have a birth certificate we can check for its age, yet we speak with confidence about it being approximately 13.8 billion years old. This isn't a guess, it's a conclusion drawn from reading the history written in the sky, a history that is inextricably linked to the universe's current, staggering size. We often think of time and space as separate things, but in cosmology, they are two threads woven into a single fabric, and the age of the universe is the key that unlocks the true meaning of its vast dimensions. The cosmos understands its own scale not by taking a snapshot, but by living a life, and its current expanse is the direct result of every moment that has passed since its fiery beginning. To grasp this, we have to confront one of the most common points of confusion about the universe. If it's only 13.8 billion years old, how can the observable universe have a radius of 46.5 billion light-years? How can something be larger than the distance light could have traveled in the time available? The answer lies in a crucial distinction, the expansion of space itself. Light from the most distant galaxies has indeed been traveling for nearly 13.8 billion years to reach us. But during all that time it has been journeying towards us. The space between that galaxy and us has been continuously stretching. The photon is like a runner on a moving treadmill that is itself getting longer. Even though the runner is moving forward at the maximum speed, the finish line is receding due to the expansion of the track. By the time the light finally arrives, the galaxy that emitted it is now much, much farther away than it was when the journey began. In fact, calculations show it is now about 46.5 billion light-years from us. The observable universe's size isn't a simple light travel distance. It's the current distance to the most remote objects whose light we can just now see, a distance that has been dramatically amplified by billions of years of relentless cosmic expansion. This elegant coupling of time and size is not a mystery to cosmologists. It is the direct prediction of the mathematical engine that drives our understanding of the cosmos, the Friedmann equations. Derived from Einstein's general relativity, these equations are the universe's own internal dashboard, displaying the real-time relationship between its age, its contents, and its scale. The key variable here is the scale factor, a number that simply tells us how much the universe has expanded compared to a previous time. Set the scale factor to 1 today, and 1 billion years ago it was a smaller number, indicating the universe was more compact. The Friedmann equations take the known densities of matter, radiation, and dark energy, and precisely calculate how this scale factor must have evolved over time. By running these equations backwards, we can find the moment when the scale factor was 0, the moment of the Big Bang, which gives us the age. By running them forward, we can understand how that initial state has stretched into the colossal volume we see today. The universe doesn't need a clock and a ruler. It has this single, self-consistent set of equations that dynamically link its past duration to its present dimensions. Its current size is literally a function of its age and its expansion history, a living, breathing record of its own life story. This transforms the cosmos from a static stage into a dynamic, evolving entity with a memory. The universe's dimensions are not a fixed number but a constantly updating readout of its own chronological journey. The size is the story. When we measure the Hubble constant, the current rate of expansion, we are taking the cosmic pulse at this very moment. When we study the cosmic microwave background, we are reading its baby picture, a snapshot of its size and structure from its infancy. When we map the large-scale distribution of galaxies, we are examining its growth into adulthood. All of these different measurements from different epochs are woven together by the thread of the Friedmann equations into a single, coherent narrative of growth. The cosmos knows how big it is because it remembers being smaller, and the physical laws that govern its expansion provide the continuous thread that connects its past state to its present condition. This isn't a metaphorical knowledge, it is a direct mathematical certainty encoded in the curvature of space-time and the flow of cosmic time, a perfect feedback loop where the universe's history is the only measurement of its scale it will ever need. Yet even this profound connection between time and space, this elegant dance choreographed by the Friedmann equations, relies on a deeper, more mysterious actor operating behind the scenes. To truly grasp how the universe continuously calibrates its own expansion, we must venture into the seemingly empty void between the stars and galaxies, for what we perceive as nothingness is, in fact, a seething, bubbling cauldron of quantum activity. This isn't a metaphorical description, it is the literal prediction of our most fundamental theories of how reality works at its smallest scales. The quantum vacuum is not a sterile, static emptiness. It is a dynamic arena teeming with a frantic dance of temporary existence. According to quantum field theory, pairs of virtual particles and their antiparticles are constantly flickering into and out of existence, borrowing energy from the void for the briefest moments allowed by the Heisenberg uncertainty principle before annihilating each other and returning the energy. This ceaseless activity is not a minor side effect. It is the fundamental ground state of the universe and its collective energy. The vacuum energy has a staggering and deeply puzzling gravitational consequence. This is where the story takes a dramatic and perplexing turn, leading us directly to the greatest mismatch between theory and observation in all of physics, the cosmological constant problem. When physicists attempt to calculate the energy density of this quantum vacuum by summing up all the contributions from every possible quantum field and every possible fluctuation mode, the result is a number so catastrophically large it defies comprehension. The theoretical prediction suggests a vacuum energy density that would be around 120 orders of magnitude. That's a 1 with 120 zeros after it, greater than the value we actually observe from measuring the universe's accelerated expansion. A vacuum energy that large would have generated a repulsive gravitational force so unimaginably powerful that it would have ripped apart every atom, every nucleus, and even space-time itself within a fraction of a second after the Big Bang. The cosmos as we know it would never have formed. Clearly, our naive calculation is wildly, spectacularly wrong. The fact that we exist in a stable, slowly accelerating universe means that the actual, observed value of the vacuum energy is almost exactly zero, but not quite. It is fine-tuned to a precision of 1 part in 10 to the 120, a level of precision so exquisite it is like hitting a target a single atom wide from the other side of the observable universe. This isn't just a mathematical inconvenience, it is a profound mystery that cuts to the heart of how the universe self-regulates. The vacuum energy, as it manifests in the cosmological constant, acts as a throttle on the expansion rate. Its value directly determines how fast the universe grows and, by extension, its ultimate scale. The fact that this value is so tiny yet positive suggests an almost impossibly precise cancellation must be happening. Somehow, the frenetic, positive energy of the quantum fluctuations is almost perfectly balanced by some other, negative energy contribution that we do not yet understand. This balance isn't something the universe measures and adjusts. It appears to be an intrinsic, built-in feature of the physical laws, a preset parameter that allows for the existence of a cosmos that can last for billions of years and develop complex structure. The quantum jitters are not a chaotic noise that disrupts the cosmic scale. They are part of a perfectly orchestrated, albeit mysterious, symphony. Their net effect is a faint, persistent background hum of energy that permeates all of space, and it is this hum that acts as the fuel for dark energy, providing the gentle, repulsive push that is currently accelerating the expansion and defining the future horizon of our observable universe. This reveals a universe that understands its scale not through active measurement, but through a deeply embedded, self-consistent balance of its most fundamental components. The quantum vacuum is not an external environment. It is the very fabric of spacetime itself, alive with potential. Its behavior, and the mysterious cancellation that renders its energy density so small, is a primary reason why the cosmos has the specific expansion history it does. The size of the universe at any given moment is therefore not just a function of its age and matter content, but also a direct reflection of this hidden vacuum energy balance. The cosmos doesn't need to calculate the effect. The effect is an inseparable part of its being, a perpetual background process that continuously influences the stretching of space simply by virtue of how quantum fields behave. This ceaseless quantum activity provides the underlying buzz of existence, a hum that subtly but surely guides the evolution of cosmic dimensions, making the vacuum not an empty stage but an active participant in the universe's silent, relentless growth. But to truly appreciate how the universe could operate with such seamless self-knowledge, we must journey back to the absolute beginning, to a moment of such inconceivable energy and density that it defies all human intuition. The Big Bang is often pictured as a giant explosion in an empty void, but that image is profoundly misleading. It wasn't an explosion in space, it was the explosive emergence of space and time themselves. In that first fleeting instant, the entire cosmos was compressed into a singularity, a point of infinite density and temperature where the known laws of physics simply break down. From that unknowable state, the universe began to expand and cool, and in doing so, it didn't just start a clock. It set in motion a chain of events whose outcome was already written into its initial conditions. The density, the rate of expansion, the precise balance of forces, these weren't random. They were the opening lines of a cosmic script that would dictate everything to come, including the ultimate scale of the entire observable reality. The universe didn't need to discover its size later because the potential for that specific size was embedded in its genetic code from the very first moment. This idea of a pre-written cosmic blueprint is thrown into sharp relief by one of cosmology's most puzzling questions, known as the flatness problem. The geometry of the universe, according to general relativity, is determined by its density. If the density is too high, space curves back on itself into a closed sphere, eventually leading to a big crunch. If the density is too low, space curves away into an open saddle shape, expanding forever into a thin, cold nothingness. But if the density is just right, at what's called the critical density, space is perfectly flat like an infinite sheet. The stunning fact is that our universe is measured to be almost perfectly flat to an astonishing degree of precision. This presents a massive fine-tuning problem. For the universe to be this flat today, its density in the first second of existence had to be fine-tuned to an accuracy of 1 part in 10 to the power of 60. That's a 1 followed by 60 zeros. To say this is unlikely is a colossal understatement. It's like balancing a pencil on its tip for billions of years and finding it hasn't fallen over. This incredible fine-tuning suggests that the initial conditions weren't accidental. They were set with a precision that seems to defy random chance, as if the size and fate of the cosmos were locked in from the very start. The resolution to this enigma is as elegant as it is mind-bending: cosmic inflation. This theory proposes that a fraction of a second after the beginning, the universe underwent a period of hyper-exponential expansion, doubling in size countless times over in an incomprehensibly short interval. This wasn't just fast growth, it was a transformative event that stretched the very fabric of spacetime itself. Imagine the surface of a wrinkled, crumpled balloon. As you inflate it to an enormous size, the wrinkles smooth out and the surface becomes increasingly flat and smooth. Inflation did exactly this to the infant universe. No matter what its initial curvature was, whether highly curved or slightly lumpy, this incredible stretching would have forced it to appear flat on observable scales. The flatness we measure today isn't a mysterious, preordained initial condition. It's the natural outcome of this violent smoothing process. Inflation didn't require fine-tuning. It actively created the conditions of fine-tuning, taking a wide range of possible starting points and processing them into the flat, uniform universe we observe. In doing so, it effectively imprinted a specific scale onto the cosmos. A scale defined by the duration and energy of the inflationary period itself. This means the universe's current vastness and geometry weren't happy accidents discovered along the way. They were predetermined outcomes, direct consequences of the physics that played out in that first fleeting moment. The initial parameters, the energy of the inflattened field, the duration of its slow roll encoded the future expansion history. The size was in the blueprint. The cosmos didn't need to later stop and measure its own diameter because that diameter was the inevitable result of its explosive birth. The inflationary model shows us a universe that, in its infancy, performed a single, monumental act of self-calibration that set the rules for the next 14 billion years of growth. The scale wasn't something to be found. It was something to be grown into, a destiny written into the source code of space-time at the moment of its creation, making the very notion of the universe needing to measure itself not just unnecessary, but fundamentally missing the point of its own exquisitely self-consistent design. But if the initial conditions of the Big Bang set the universe's trajectory and its inflationary growth spurt locked in its fundamental parameters, then how does this vast cosmic system maintain a continuous, coherent sense of its own scale across billions of years? It doesn't need to constantly recheck its dimensions because it possesses something far more elegant, a form of cosmic memory. This isn't a memory in the human sense of recollection. It's the persistent, indelible imprint of past physical states onto the present structure of reality. The universe isn't an amnesiac, it is an impeccable archivist, and its most important records are not stored in some dusty library, but are written across the sky itself and woven into the very fabric of spacetime. The most profound and accessible of these archives is the cosmic microwave background radiation. We've spoken of it as a fossil, but that analogy sells it short. A fossil is a static remnant, a bone turned to stone. The CMB is more like a living, breathing birth certificate that continues to dictate the present-day anatomy of the cosmos. Those tiny fluctuations in temperature, those faint patterns of hot and cold that we map with such precision, are not just a snapshot of what the universe looked like at age 380,000 years. They are the active seeds from which the entire cosmic web of galaxies and voids grew. The specific statistical properties of those patterns, the preferred size of the hotspots, their distribution, their correlation across the sky encode critical information about the universe's early size, its composition, and its rate of expansion at that epoch. This information isn't locked away, it is actively being used. The gravitational potential of those denser regions pulled in matter for billions of years, dictating where galaxies would form and how they would cluster. The universe's current large-scale structure is the direct, evolved manifestation of that memory. It doesn't need to remeasure its scale because its current architecture is the measurement, a living monument to its own initial conditions. The pattern is the data, and the galactic distribution is the processed result. Yet the universe, in its wisdom, keeps more than one kind of record. While the CMB is a stunningly detailed photograph of the universe's early childhood, there may be an even older, fainter echo waiting to be detected: primordial gravitational waves. These would be ripples in the fabric of spacetime itself, generated by the incredibly violent energy of the inflationary expansion. If the CMB is a light wave fossil, these gravitational waves would be a spacetime fossil, a vibration from the universe's first trillionth of a second of existence. Their detection would open a window into an epoch even before the CMB was created, a time when the universe's scale was being set in that furious exponential growth. The specific properties of these waves, their frequency and amplitude, would tell us directly about the energy scale of inflation. A stronger signal would indicate a more violent, higher energy inflationary period, which would inherently correlate to a different initial calibration of the cosmic scale. Finding these waves would be like discovering the universe's very first diary entry, written not in light or matter, but in the pure geometry of space-time, preserving a memory of its size from a time before there was anything else. This concept of cosmic memory extends beyond these specific fossils to the overarching symmetry of the cosmos itself. The large-scale isotropy and homogeneity of the universe, the fact that it looks the same in every direction and that matter is evenly distributed on the grandest scales, is itself a form of persistent, stable memory. This uniformity isn't a coincidence, it is the preserved outcome of inflation's incredible smoothing power. It is a continuous background fact that defines the rules of the game everywhere. Because the universe is homogeneous, the laws of physics are the same here as they are 10 billion light-years away. This consistency means that the relationships that define scale, the gravitational constant, the speed of light, the fine structure constant, operate identically across the entire observable volume. The universe doesn't have regional variations in its fundamental rules that would require constant recalibration. Its unwavering uniformity is a form of active, eternal memory, ensuring that a light year measured in one galaxy means exactly the same thing in another. The cosmos remembers to be consistent, and in doing so, it maintains a stable, knowable scale across all of space and time. This reveals a universe that is profoundly self-referential and self-consistent. Its past is not a separate country, it is an active participant in shaping the present. The initial conditions are not forgotten data points, they are the foundational code that is still running. The universe knows its size because that information was imprinted at the beginning and has been faithfully preserved and expressed through the evolution of its structures and the constancy of its laws. There is no need for a continuous, active measurement because the entire system is a closed loop. The laws dictate the evolution, and the evolved state reflects the initial conditions that the laws acted upon. The memory is in the pattern, the structure, and the very symmetry of existence, making the cosmos not a blank slate but a palimpsest, with the story of its origin and scale written and rewritten into every galaxy, every void, and every photon that has traveled since the dawn of time. So we find ourselves in a universe that remembers its past, carrying the imprints of its initial conditions forward through time in the structure of galaxies and the uniformity of physical law. But this profound self-consistency raises an even more fundamental question, one so basic we almost never think to ask it. Why does our universe have the specific shape that it does? We move through a world of three spatial dimensions: length, width, and height, a reality so ingrained in our experience that imagining anything else feels like a purely mathematical exercise. Yet this number 3 is not an arbitrary default setting. It is a critical, foundational parameter that actively defines the very possibility of a stable, complex cosmos. The dimensionality of space isn't just the stage upon which the drama of the universe unfolds. It is the director that dictates the entire plot, from the orbits of planets to the very forces that hold atoms together. To understand why, let's take a thought experiment into a universe with just two spatial dimensions. Imagine a flatland, a world of only length and width, like a drawing on an infinite sheet of paper. In this reality, life would be profoundly limited. The digestive system of any complex creature would literally cut it in half, separating its front from its back. But more crucially for the cosmos, the laws of physics would operate differently. In a two-dimensional universe, the force of gravity wouldn't follow the familiar inverse square law we know. Its strength would diminish much more slowly with distance. This has a catastrophic consequence for stability. A star in a two-dimensional universe could not hold planets in stable, elliptical orbits. The slightest perturbation would send a planet either spiraling in to be consumed or flying off into the void. The beautiful clockwork dance of our solar system, which provides a stable environment for life to evolve over billions of years, would be impossible. The very concept of a long-lived, structured cosmos depends on having enough dimensions to allow for stable, bounded orbits. Now, let's add a dimension and consider a universe with 4 spatial dimensions. At first, it might seem like more room would mean more possibilities, but for the forces that govern reality, it would be a recipe for instant dissolution. In 4 dimensions of space, gravity would obey an inverse cube law. its strength fading away so rapidly with distance that it would be incredibly weak. A sun would struggle immensely to hold onto its planets. The orbits would be wildly unstable, prone to collapsing or escaping with the slightest nudge. But the problems run even deeper than that. In our three-dimensional world, the fundamental forces are perfectly tuned. The electrical force that holds electrons in orbit around a nucleus and the strong nuclear force that binds protons and neutrons together are precisely calibrated to allow for the existence of stable atoms. In a higher dimensional space, the behavior of these forces changes. The delicate balance that allows for complex atomic nuclei and the rich chemistry of life would likely be shattered. Atoms might not be able to form at all, or they would be so unstable that matter as we know it could never coalesce. The three spatial dimensions we inhabit appear to be a Goldilocks number, not too few, not too many, that allows for both the large-scale stability of galactic structures and the small-scale stability of atomic structures, creating a narrow window of possibility where a universe can be both vast and complex. This concept of hidden dimensions moves from philosophical speculation to a concrete, mathematical framework in the realm of string theory. This ambitious attempt to unify all forces of nature proposes that the fundamental building blocks of reality are not point-like particles but unimaginably tiny, vibrating strings. For the mathematics of string theory to be consistent and to naturally include gravity, it requires more than the three spatial dimensions we see. It needs 10 or 11. So where are these extra dimensions? The theory suggests they are compactified or curled up into a space so incredibly small, on the order of the Planck length, that they are completely hidden from our perception. The way these dimensions are curled up, their specific geometric shape and size isn't just a technical detail, it is everything. It directly determines the effective laws of physics in the three-dimensional universe we experience. The charge of an electron, the mass of a quark, and crucially, the relative strengths of the fundamental forces are all set by the geometry of these hidden dimensions. This means the scale of our entire observable universe is, in a very real sense, a secondary effect. The primary reality is the full, higher dimensional space. The three vast dimensions we move through and the forces that operate within them are a kind of shadow, a projection of the intricate, compactified geometry happening at the smallest possible scale. The strength of gravity, which sets the scale for everything from planets to galaxy clusters, is not a fundamental constant in its own right. It is an emergent property, a consequence of how the graviton, the particle that carries the gravitational force, is able to propagate through the full 10-dimensional space, including how it leaks into or is confined by the curled-up dimensions. The size we measure with our telescopes is therefore a direct consequence of the size and shape of these unseen dimensions. Dimensionality itself is the ultimate arbiter of scale, setting the rules of the game from which all other measurements inevitably follow. But this breathtaking fine-tuning of our three spatial dimensions, this perfect balance that allows for both atomic stability and cosmic structure, leads us to an even more profound realization about the nature of reality. We tend to see the universe as a place of either stark order or random chaos, a cosmos that is either meticulously planned or wildly accidental. Yet the truth that emerges from the deepest study of physics is something far more fascinating and nuanced. The universe is a complex system, a vast and dynamic network where breathtaking order and intricate patterns arise spontaneously from the bottom up, emerging from the simple, local interactions of countless individual parts, all without any central planner, blueprint, or overarching measurement process. It is a system that self-organizes, finding its own equilibrium and structure through the relentless and blind application of a few fundamental rules. We can see this magnificent self-assembly at work across every scale of existence. Consider the force of gravity, the great sculptor of the cosmos. Its rule is stunningly simple. Every bit of matter attracts every other bit of matter. There is no grand design document for a spiral galaxy. There is no cosmic architect directing where each star should go. Instead, a vast cloud of primordial gas, governed by nothing more than this single, simple rule of attraction, begins to collapse. Tiny, random fluctuations in density, those quantum seeds left over from inflation, act as nucleation points. Gravity amplifies them. Denser regions pull in more matter, growing denser still. As the cloud collapses, conservation of angular momentum causes it to spin and flatten into a disk. Within that disk, further instabilities lead to the clumping that forms individual stars and planets. From a near-featureless haze, a magnificent, structured galaxy emerges, complete with spiral arms, a central bulge, and a halo of dark matter. The entire process is a beautiful, inevitable domino effect, a chain reaction of cause and effect driven by one simple law. The universe didn't need to measure the correct distance between stars or calculate the optimal rotation rate for the disk. The final, ordered structure is an emergent property, an output generated by the system itself as it follows its ingrained programming. This phenomenon of emergent order isn't confined to the grandest scales. Look at the seemingly chaotic churn of a turbulent fluid or the violent swirl of interstellar gas clouds. To the naked eye, it appears as pure, unstructured chaos. But when physicists analyze these systems, they discover something astonishing hidden within the apparent randomness, deep and precise mathematical order. These systems often exhibit fractal patterns, intricate structures that display self-similarity across a vast range of scales. A small eddy in a stream has the same characteristic shape as a massive whirlpool in an ocean current. The branching pattern of a lightning bolt mirrors the branching pattern of a river delta, and even the branching pattern of the neurons in your brain. This is known as scale invariance, a property where the same statistical patterns and geometric qualities repeat themselves regardless of how much you zoom in or out. The universe isn't imposing this pattern from the top down. It is a natural signature of complexity emerging from simple, iterative processes. It is the mathematical footprint of a system left to its own devices, organizing itself according to its internal logic. The pattern is the system's knowledge of how to be. No external measurement or design is required for it to express this profound, embedded order. This capacity for self-organization creates a rich hierarchy of structures, a nested set of realities within realities. From the quantum foam flickering at the Planck scale, to the stable orbits of electrons around a nucleus, to the complex chemistry of a living cell, to the gravitational dance of planets around a star, to the swirling majesty of a galaxy, and finally to the vast, web-like architecture of the cosmic supercluster network, each level of complexity emerges from the one below it. A planet doesn't know it's part of a solar system. It just responds to the gravity of its star. A star doesn't know it's in a galaxy. It just follows the collective gravitational field of the billions of stars around it. And a galaxy doesn't know it's part of a filament in the cosmic web. It simply moves along the gravitational topography dictated by the dark matter distribution. At no point does the universe need to stop, take a census, calculate the center of mass for a supercluster, and then assign positions. The entire, magnificent hierarchy is the inevitable outcome of local interactions propagating upward, creating global order from local rules. The cosmos builds itself from the ground up, with each component mindlessly obeying a small set of instructions, resulting in a whole that is infinitely greater and more complex than the sum of its parts. This bottom-up, self-referential architecture is the universe's way of managing its immense complexity without any need for a central processor or an external measuring stick. But if the universe is this stunningly complex, self-organizing system that builds its own structure from the bottom up, then what is the fundamental mechanism driving it all? What is the engine of reality? This leads us to a radical and captivating idea, one that reframes the entire cosmos not as a collection of objects in space, but as an ongoing, dynamic process of information processing. Imagine the universe as the most powerful computer imaginable, not one made of silicon and wires, but one whose hardware is the very fabric of space-time and whose software is the immutable laws of physics. In this view, every particle interaction, every gravitational dance, every flash of light is not just a physical event but a computational step. The universe is not a static thing that has a size. It is a dynamic system that is continuously computing its state, and its current dimensions are simply the most recent output of that endless, pervasive calculation. This perspective, known as pancomputationalism or the theory of digital physics, proposes that computation isn't just something we do with machines. It is a fundamental principle of nature, as basic as energy or entropy. The laws of physics, from the elegant equations of general relativity to the probabilistic rules of quantum mechanics, are not merely descriptions of behavior, they are the algorithms themselves. They are the code that the universe is running. Gravity isn't just a force, it's an algorithm that calculates the curvature of space-time based on the distribution of mass and energy. Quantum field theory isn't just a model. It's the operating system that governs how quantum states evolve and interact. In this grand computational framework, the universe doesn't need an external programmer or a user to input commands. It is a self-contained, self-processing system. Its initial conditions were the input, and the laws of physics are the program that has been executing for nearly 14 billion years. With every passing moment representing a new cycle in the cosmic processor. So how does this computational view make the concept of measurement obsolete? Think about how a video game engine creates a vast, open world. The game world isn't a pre-rendered, static map that the computer loads in its entirety. That would be impossibly inefficient. Instead, the world is generated procedurally. The computer uses a set of algorithms and a seed number to generate the terrain, the trees, the buildings, and the characters only when and where the player is looking. The world doesn't have a fixed, pre-measured size stored in memory. Its size is an emergent property of the procedural generation rules. The universe might be operating on a similar principle. The cosmos isn't storing a giant lookup table with the position of every atom. Instead, it's running a program whose output is the continuous, consistent evolution of quantum fields and the curvature of spacetime. The size of the observable universe isn't a measured value held in a cosmic register. It is the current result of the cosmological equations being solved in real time by the universe itself. The expansion is the computation. The distribution of galaxies is the output. We, as conscious observers within the system, are simply accessing the current frame buffer of this magnificent simulation. This idea finds its most profound expression in the holographic principle, which we can now reinterpret not just as a physical theory, but as the ultimate data compression scheme. If the universe is a computer, then the holographic principle tells us about its astonishingly efficient memory architecture. In a conventional computer, the amount of memory required to simulate a volume of space would be proportional to the number of points within that volume. But the holographic principle reveals a far more elegant and mind-bending truth. All the information needed to describe a three-dimensional volume of space can be encoded on its two-dimensional boundary. It's as if the universe is a cosmic projector, and the three-dimensional world we experience is a movie being shown on the inner surface of a giant spherical screen. The events within the volume, the motion of planets, the fusion of stars, the thoughts in our brains are not the primary reality. They are a projection, a rendering of the information stored on the boundary. This means the universe's computational load is vastly lighter than we might have imagined. It doesn't need to compute the state of every point in a volume. It only needs to compute the state of the data on the surface, and the rich three-dimensional reality emerges as a consequence. The size of the universe, in this view, is directly tied to the information capacity of that outer surface. It is not measured, it is rendered. This breathtaking shift in perspective, from a universe that is to a universe that computes, naturally forces us to re-examine our most fundamental concepts. If reality is a computation, then what are time and causality? We typically think of time as a flowing river carrying events from the past through the present and into the future. Causality is the unbreakable chain that links cause to effect. But in a computational framework, these concepts take on a different flavor. Time may not be a fundamental flow at all. It could be an emergent property, the sequence of steps in the cosmic computation. Each tick of the universe's processor could correspond to a Planck time, the smallest meaningful unit of duration. The arrow of time, the reason we remember the past and not the future, could be a consequence of the increasing complexity of the data being processed, much like the increasing entropy we see in thermodynamic systems. The universe is computing its way from a state of low complexity and high symmetry, the hot, dense Big Bang, toward a state of high complexity and intricate structure, the galaxies and brains of today. Our perception of time's flow is our experience of moving through this computational sequence. Causality, the bedrock of classical physics, also gets a fascinating makeover. In a deterministic universe computed by classical laws, the future state is entirely determined by the past state. It's a giant, pre-computed movie, but quantum mechanics injects an element of genuine unpredictability. The universe's quantum computer doesn't calculate a single, definite outcome. It calculates a spectrum of probabilities. The collapse of the wave function, which gives us a definite reality, might be the moment a probability is resolved into a specific data point. This suggests that causality at the quantum level isn't a rigid chain of billiard balls hitting each other, but something more like a probabilistic inference within the computation. The universe isn't calculating what will happen. It's calculating the likelihood of countless possibilities, and our observed reality is one branch of that ongoing calculation. This doesn't break causality, but embeds it within a more complex, informational framework where the relationship between events is about data dependency and logical inference, not just brute force sequence. The cosmos is not a clockwork mechanism. It is a quantum computer processing exabytes of information every moment, and the laws of physics are the elegant, efficient code it uses to maintain a consistent and stable reality from one Planck time to the next. But if the universe is a computer processing information, then what is the nature of the processor itself? We've arrived at a point where our physical descriptions brush up against the deepest philosophical questions we can ask. Does the universe actually know its own size in any meaningful sense? Or are we simply projecting our own human experience of consciousness and intention onto a vast, mindless, mechanical system? This isn't just wordplay, it's a fundamental inquiry into the nature of reality. Are we living in a universe that possesses a form of intrinsic awareness? Or are we simply mistaking the breathtaking, self-consistent complexity of physical law for a kind of intelligence? This is the frontier where physics meets metaphysics, and the answers we lean toward reshape our entire conception of existence. One compelling perspective comes from a school of thought known as panpsychism. This ancient idea, which is finding new resonance in modern philosophy of mind, suggests that consciousness is not a rare and late-breaking product of complex biological computation. Instead, it proposes that consciousness is a fundamental property of the universe, as basic as mass or charge. In this view, even the most elementary particles, electrons, quarks, might possess an infinitesimal, primitive form of experience or proto-consciousness. The argument is one of continuity. We, as conscious beings, are made of particles. If consciousness emerges only at a certain level of complex arrangement and suddenly switches on, that seems like a magical, arbitrary threshold. Panpsychism avoids this by suggesting that consciousness is everywhere, but it's only in highly complex, integrated systems, like a human brain, that it combines into the rich, flowing stream of awareness we recognize. From this vantage point, the universe doesn't just blindly obey mathematical laws. It has an interiority. Its self-knowledge of its size and constants wouldn't be a metaphorical flourish. It would be a literal, though undoubtedly alien, form of awareness. The cosmos wouldn't be calculating its dimensions. It would be feeling them, experiencing the stretch of its expansion and the curvature of its spacetime as a fundamental aspect of its being. The stark opposite of this view is the philosophy of eliminative materialism. This position argues that we are making a category error by using words like know or aware in this context. These are psychological terms that apply to humans and some animals, and they have no business being applied to the cosmos. From this perspective, the universe doesn't know anything. It just is. It operates with flawless mathematical precision because that is what the laws of physics dictate. The fact that these laws are self-referential and yield a consistent, measurable scale is a feature of the system's logic, not evidence of any kind of mind or intention. To say the universe knows its size is like saying a pocket calculator knows how to do arithmetic. The calculator is just following its programming, and the universe is just following its physical laws. The appearance of knowledge is an illusion, a pattern we recognize because we are pattern-seeking creatures. In this view, the search for why the universe is the size it is may be a pointless one. It's like asking why the number pi has the value it does. It doesn't have a reason. It simply is a necessary consequence of the definition of a circle in Euclidean geometry. The universe's scale might be the same, a brute fact, not something to be known, but something that simply exists as part of the unchanging framework of reality. This profound debate forces us to confront the very nature of measurement itself. We've spent this entire video exploring how the universe doesn't need to measure itself in the way we do. But perhaps the deeper truth is that all measurement is ultimately a human construct. Think about it. A meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole. A second was defined as a fraction of a day. These are human-centric, arbitrary units. We then project these units onto the cosmos and are amazed when the universe doesn't need them. But the constants we discover, the speed of light, the gravitational constant, are not measurements by the universe. They are just constants. They are fixed parameters in the equations of reality. The universe isn't measuring itself against them. It is operating according to them. The concept of measurement implies a separation between the measurer and the measured, a subject and an object. The universe is both. It is the ultimate unified system. Our human act of measurement is our way of interacting with that system, of translating its intrinsic properties into our limited language of numbers and units. But the system itself is complete and whole, requiring no such internal translation. It doesn't contain rulers. It contains relationships, and our rulers are just clumsy attempts to make those relationships tangible. This suggests that the universe's self-knowledge isn't an active process but a state of being. It is congruous with itself. Its size is congruent with its age, its constants, and its laws because they are all part of one inseparable, self-consistent whole. The mystery isn't how it knows itself, but that it is at all a unified, knowable system. So we arrive at the ultimate, almost unaskable question that has been lurking beneath the surface of our entire journey. We've explored how the universe encodes its scale in its constants, expresses it through its expansion, and embodies it in its geometry. But when we say the universe knows its own size, what are we really saying? Are we using a convenient metaphor, a poetic shorthand for a complex physical process, or are we brushing up against a profound truth about the nature of reality itself? This isn't just semantics, it's the fundamental divide between seeing the cosmos as a mindless, mechanical system and perceiving it as something more, a system that possesses, in some form, an inherent awareness of its own existence. One of the most audacious and ancient ideas that speaks to this possibility is panpsychism. This philosophy suggests that consciousness is not a rare and miraculous accident that emerged solely in the wetware of complex animal brains. Instead, it proposes that consciousness is a fundamental and ubiquitous feature of the universe, as basic as space, time, or mass. In this view, even the most elementary particles, electrons, quarks, photons, might possess an infinitesimal, primitive form of experience or proto-consciousness. It's not that an electron is thinking, that would be absurd, but perhaps it has a faint interior dimension, a mere whisper of what it is like-ness that is utterly alien to our own rich human consciousness. The panpsychist argument is one of elegant continuity. We, as conscious beings, are made of particles that were once part of stars. If consciousness is not fundamental, then at what precise point in the assembly of atoms into molecules and molecules into neurons does this miraculous switch get flipped? Panpsychism avoids this hard problem by distributing it everywhere, suggesting that the human mind is not a generator of consciousness, but a highly complex collector and amplifier of it. From this vantage point, the universe's self-knowledge of its size isn't a metaphor. It is a literal, though incomprehensibly diffuse, form of cosmic sensation. The expansion of space isn't just a geometric fact, it is felt. The curvature around a planet isn't just a mathematical quantity, it is experienced. The cosmos in its entirety might be a vast, integrated field of experience, and its consistent laws and scales are the external signature of this deep, internal awareness. Standing in direct opposition to this view is the philosophy of eliminative materialism, which argues that we are making a profound category error by using psychological language to describe physical processes. This position holds that terms like know, aware, or conscious are useful only for describing the behavior of certain complex biological organisms. Applying them to the universe at large is a form of intellectual anthropomorphism, projecting our own human experience onto a vast, mindless, and utterly impersonal clockwork. For the eliminative materialist, the universe doesn't know anything. It just is. It operates with flawless mathematical precision because that is the inevitable consequence of its initial conditions and the immutable laws of physics. The fact that these laws are self-referential and yield a consistent, measurable scale is a feature of the system's cold, hard logic, not evidence of any kind of mind or intention. To say the universe knows its size is like saying a river knows how to flow downhill to the ocean. The river is simply obeying gravity. It possesses no interior knowledge of its path. Similarly, the cosmos is simply executing its programming. The breathtaking consistency we observe is the beautiful, but entirely mindless, output of a set of equations playing themselves out across billions of light years. In this view, the search for a why behind the universe's scale is as pointless as asking why the number pi has the value it does. It doesn't have a reason. It simply is a necessary consequence of a deeper mathematical truth. This chasm between these two worldviews forces us to confront the very nature of measurement itself. We've spent this entire exploration detailing how the universe doesn't need to measure itself with external tools. But perhaps the most radical realization is that all measurement is, in the end, a human construct. Think about the units we use. A meter was originally 1/10,000,000th of the distance from the equator to the North Pole. A second is a fraction of a day. These are parochial, Earth-centric, and deeply arbitrary standards. We then project these human inventions onto the cosmos and are amazed to discover that the universe operates perfectly well without them. The constants we uncover, the speed of light, the gravitational constant, are not measurements by the universe. They are simply its fixed operational parameters. The universe isn't measuring itself against them. It is functioning according to them. The very concept of measurement implies a separation between the observer and the observed, a subject and an object. But the universe is the ultimate unified system. It contains both. There is no outside vantage point from which to take the measurement. Our human act of scientific measurement is not us discovering how the universe measures itself. It is our way of interacting with a complete and self-contained system, of translating its intrinsic, relational properties into our own limited language of numbers and units. The system itself requires no such internal translation. It doesn't contain rulers, it contains relationships, and our rulers are just our clumsy attempts to make those relationships tangible and meaningful to us. This suggests that the universe's self-knowledge isn't an active process but a state of being. It is congruous with itself. Its size is perfectly congruent with its age, its constants, and its laws because they are all inseparable aspects of one unified, self-consistent whole. The true mystery, then, isn't how it knows itself, but that it is at all a unified and intelligible system that we can partially understand. Yet for all the profound theories and elegant equations, the ultimate validation of how the universe understands its own scale will not come from pure thought alone, but from the relentless, meticulous work of observation and experiment. We stand on the precipice of a new golden age of cosmology, armed with tools of such staggering sensitivity that they promise to peer deeper into the cosmic dawn than ever before, potentially uncovering the primordial signatures of this self-knowledge written into the fabric of reality. The James Webb Space Telescope is not merely a more powerful version of Hubble. It is a time machine designed to capture the faint infrared glow of the very first stars and galaxies that ever formed. By studying these infant structures, we are effectively reading the universe's own baby book, looking for clues in their size, distribution, and composition that tell us about the initial conditions from which they grew. The specific pattern of how matter first clumped together is a direct echo of those quantum fluctuations amplified during inflation, and by measuring this pattern with exquisite precision, we can reverse engineer the physics of that explosive beginning. This allows us to test whether the universe's current vast scale was indeed pre-programmed by the dynamics of that first fraction of a second, moving from philosophical speculation to hard, observational evidence. Beyond the realm of light, a completely new window onto the cosmos is being thrown open with the advent of gravitational wave astronomy. Observatories like LIGO, Virgo, and the future space-based LISA mission are listening to the universe. They are tuning in to the ripples in spacetime itself caused by the most cataclysmic events, like the mergers of black holes and neutron stars. But the holy grail of this field is the detection of primordial gravitational waves, faint ripples generated not by stellar collisions, but by the violent energy of the inflationary expansion itself. Finding this signal would be like discovering the universe's very first breath, a vibration from a time when all of reality was smaller than a single atom. The properties of these waves, their frequency and amplitude, would tell us directly about the energy scale of inflation. A stronger signal would point to a more violent, higher energy inflationary period, which would inherently correlate to a different initial calibration of the cosmic scale. Detecting these waves would provide a direct, uncontestable link between the universe's unimaginably small beginning and its current immense size, offering perhaps the most compelling evidence yet that its dimensions were encoded at birth, not measured later. While our telescopes peer outward and our gravitational wave detectors listen in, theorists are engaged in a parallel monumental effort to develop a complete theory of quantum gravity, a framework that can seamlessly unite the vast, geometric realm of general relativity with the fuzzy, probabilistic world of quantum mechanics. This is the final frontier of fundamental physics, and its success would revolutionize our understanding of space, time, and scale. Leading candidates like string theory and loop quantum gravity are not just attempts to fix a mathematical inconsistency, they are quests to discover the universe's ultimate operating system. These theories strive to describe the nature of reality at the Planck scale, where the very concepts of distance and duration break down into a quantum foam. Within these frameworks, the familiar three-dimensional space we inhabit and its associated size is not fundamental. In string theory, it emerges from the vibrations of tiny strings in higher dimensional space. In loop quantum gravity, it emerges from a network of discrete, quantized loops of spacetime. The profound implication is that the universe's large-scale dimensions are an emergent property, a collective effect that arises from countless underlying quantum events. A successful theory would show us precisely how this emergence works, providing equations where the concept of size naturally unfolds from more primitive, non-spatial building blocks, finally rendering the idea of the universe needing to measure itself completely obsolete. It would reveal that scale is not a primary quality but a secondary, derivative phenomenon, the grand and stable illusion born from a hidden, microscopic reality. And then there is the most speculative, yet scientifically compelling, avenue of all, the search for evidence of a multiverse. If our universe is just one bubble in a vast cosmic foam, then its specific size and constants become local accidents rather than cosmic necessities. The pursuit here is twofold. First, could we ever detect evidence of another universe? Some theories suggest that if our universe collided with another bubble in the multiverse in the distant past, it might have left a detectable imprint on the cosmic microwave background, a kind of cosmic bruise on the sky. While searches for such an anomaly have so far come up empty, the quest continues, a testament to the audacity of the idea. The second approach is through massive computer simulations. By modeling the physics of eternal inflation or the string theory landscape, scientists can explore how universes with different properties, including vastly different sizes, naturally arise. These simulations don't create universes, of course, but they allow us to study the statistical distribution of possible realities. If we find that life-permitting universes like our own are a predictable, even common, outcome within a certain range of parameters, it would profoundly change our perspective. It would suggest that our universe's scale isn't a unique, knowable fact from a single perspective, but simply one data point in a much larger, perhaps infinite distribution. The mystery of cosmic self-knowledge would then expand from a question about one universe to a question about the meta-laws that govern the entire multiversal ensemble, a puzzle of breathtaking scope that ensures the pursuit of understanding will continue to drive human curiosity for generations to come. So after this incredible journey through relativity, quantum foam, and cosmic horizons, what is the ultimate takeaway? It's this: the universe doesn't measure itself. It embodies its own scale. It doesn't use tools, it is the tool. From the very first instant, its size was never a question to be answered, but a property to be expressed. The fundamental constants, the speed of light, the strength of gravity, the value of the cosmological constant, these aren't numbers on a cosmic dial that the universe consults. They are its immutable identity, the fixed settings that inherently define every relationship between energy, space, and time. The expansion isn't a process that reveals size, it is the very mechanism of defining it in real time. A dynamic, self-referential act where the motion of galaxies is both the action and the data. The quantum vacuum isn't an empty stage but an active participant, its seething fluctuations subtly guiding the expansion through a mysterious, pre-programmed balance. And the holographic principle suggests that the three-dimensional volume we move through might just be a magnificent projection, an illusion of depth emerging from information encoded on a distant, two-dimensional surface. In every one of these ways, the cosmos operates as a closed, intelligent loop. Its laws are self-referential, its constants are self-defining, and its history is a continuous unfolding of a reality that was always complete, always consistent, and always aware of itself in a way that transcends any human concept of measurement. This isn't just a different way of doing science, it's a different way of perceiving existence. It challenges the very core of what we think it means to know something, suggesting that true knowledge isn't always an external acquisition, but can be an intrinsic, embedded state of being. The universe knows itself by being itself. Every law is a form of self-awareness, every constant is a declaration of identity, and every photon traveling across the void is a silent testament to a cosmos that is not a silent, empty expanse, but a profoundly coherent and self-understanding system. So the next time you find yourself under a clear night sky, looking up at those countless points of light, try to shift your perspective. You are not just an observer looking out at a vast and distant universe. You are a part of the universe itself, looking back at itself, witnessing its own immense, self-knowing grandeur. It's a perspective that transforms awe into understanding, and wonder into a deep, humbling connection with the intelligent cosmos we call home. We'd love to hear which part of this cosmic mystery resonated most with you. Was it the holographic universe, the self-defining black holes, or the eerie perfection of the fundamental constants? Let us know your thoughts in the comments below, and if you enjoyed this deep dive into how reality works, be sure to subscribe and hit the bell so you don't miss our next journey into the universe's greatest mystery.